Oh, you download it? Yeah, if you got it from GitHub, you just go into the doc directory and type make nb convert. Yeah, so let me go down here and show you how it works. So if you're in the doc directory, you do make nb convert, and that'll create all those notebooks for you in the directory. I'll change all the versions. Hopefully I made this as easy as possible. We'll see. Okay, so why don't we get started? We're the way I'm going to work is I'm going to have this web page up in one tab. I'm going to have the notebooks up in another tab, and then I'm also going to have my terminal that I'll come to occasionally, but we probably won't have to use the terminal very much throughout today. So if you can get your tabs set up so you have the web page here and the notebook, that would be great. And I'm going to make it full screen here. Okay, so as by way of introduction, the machine learning, I think, is a tool that can be useful in a lot of different fields. It's been used in a lot of different fields, and my hope is that everybody here, no matter what sort of data you're working with and what sort of application you have, you'll be able to use the tools that we talk about here and work with them within your own field. A few people walking in. Did everyone get the memory stick? There are a couple memory sticks being passed around. Where did they end up? I think there's a few new people that need them. The memory stick has some data files on it that we'll be using a little bit later. Okay, so I think most of I'm going to click on tutorial setup installation right now. I think most of what I've said already is in here, and hopefully everyone has these prerequisites installed. This download the datasets part, running the fetch data.py, you don't need to do that if you got everything from the little memory stick I was passing around. That already had the datasets there. So let's go on to the next and get into the content. So let's talk about general concepts. So for this first section, I want to make sure that so Scikit-Learn, when you're dealing with data, it expects a certain data format. And so we're going to talk a little bit about how you might extract features from real-world data that can be used in that format. And it's a simple format. It's just a matrix, the number of features by the number of samples by the number of features. So every data set in Scikit-Learn is expected to be a two-dimensional array, essentially. So here we're also going to talk about the difference between supervised learning, which includes classification and regression on one hand, and on the other hand, we're going to talk about unsupervised learning, which is things like dimensionality reduction, clustering. It can be useful for data visualization and things like that. And also, we're going to play around and understand the difference between a problem that's linear and a problem that's nonlinear, because that ends up being important. So basically, this plot right here shows you basically what machine learning is all about. You have two data sets, or you have one data set that has some different labels, and you're trying to find some way to classify them. This is what we would call a classification problem, where you have, it's one big data set in 2 dimensions, and we can plot it on a graph like this. The colors are the labels of each point, and one machine learning task might be asking to find the best dividing line between these two classes. So this is a typical classification problem, and we'll get into that later. Just a side note, if you're ever curious, any of the images in this tutorial, you can click on them, and it has the Python code that was used to generate them. So in case you want to see the nitty-gritty of how things were put together. So let's talk first about features and feature extraction. So as I said before, every every data set in Scikit-Learn is assumed to be a matrix or an array, a two-dimensional array. That's the number of samples by the number of features. So that's the shape of the array. And by number of samples, I mean different objects. So we're going to be talking about astronomy later. So maybe the number of samples would be the number of galaxies or the number of stars you observe. And then the number of features is independent measurements you have of each of those objects. So if you're looking at stars, you might take an image of that star through a red filter, through a blue filter, through a green filter, and a yellow filter, say. So then you would have 4 features for each object, and you might observe 1 million galaxies, so that would be 1 million samples. So your data set would end up being a 1 million by 4 array. So that's typically what Scikit-Learn expects. So we'll do a quick example here, and Scikit-Learn has a number of basic examples that data sets that are just built in that we can play with. So we're going to go to the first notebook, the datasets.ipynb, and click on that, and we'll see this right here. So this will just show you basically how to work with data from the Scikit-Learn. So we're looking at data from the iris data set. So this is observing the characteristics of a bunch of flowers in nature. And based on what the characteristics of those flowers, we're trying to classify what species those flowers belong to. Yeah, if you go, so once again, the IPython notebook, if you change directory to the notebooks directory, either in the GitHub repository or in that file that I gave you on the data stick, and then you type IPython notebook and press enter, you should see this page right here. Everyone good? Cool. So once again, you click on the first one, data sets, and we'll see this right here. Nope, not that. This. So we're looking at irises, flowers with different features, and the features in this data set are the length of petals and sepals, various parts of the irises. You know, scientists went out and measured those with a ruler, I guess. That's how you'd measure irises. And so there are 4 features, and then the targets are one of 3 different species. So the first thing we do is from sklearn.datasets, we import load iris and then call that. And this will load the iris dataset. And just as an aside, if you want to see what other datasets are available, you can just type sklearn.datasets ? And then, actually, sklearn.datasets dot and then press tab. What did I do wrong here? I did. Yeah, there it is. Dot tab. I'm doing something wrong. We'll see that later. Sorry about that. Okay, so we've loaded the iris data set, right? And we're going to look at what the number of samples and the number of features are in this data set. So that's in the data attribute. That's the array where the data is kept. And the shape is the number of samples and number of features. So we see there are 150 samples, 4 features. And if we look at the first sample, these are what the features are. So basically the sepal length is 5.1 centimeters, the petal length is 1.4 centimeters, etc. So that's what we're looking at. This is how we've taken our real-world data set and put it into a format that Scikit-Learn can use. Okay?
I'm sorry to get
Yeah.
away. When I open up the notebook, I just get a blank thing, even though I click on the data set. Is there some obvious thing I'm supposed to do?
Do you have try loading the version 2 of it, because you might be running an older IPython. So yeah, if you're running an older version of IPython, you might need to click on .v2 to make that pop up. Does that work for you?
I
running no script, or no script off.
No script?
No script, you need a JavaScript blocker. You have to turn that off.
Oh, really? Okay.
You have to run JavaScript.
Okay, so maybe that's the problem. Are you blocking JavaScript? Or? Okay, thanks.
I had a similar problem. I just upgraded to 13.
Oh, really? Okay.
This is the old one.
Okay. So I think one person said if they had that problem, they upgraded to 13 and it was okay. Okay, so we're looking. We have the iris.data, which is those set of feature measurements, and then the iris.target is the set of applications for the training set. So we look at the length of those two. They're the same, which is good. And looking at the target, it's basically a numerical classification, and this is pretty common in Scikit-Learn too. You know, we don't have a way we don't want to put an array with the name of each of those species. We don't want an array full of iris setosa, iris versicolor, because it's not numerical. The method wouldn't know what to do with it. So we encode those features as basically, or those classifications as numbers, either 0, 1, or 2. And in the iris data set, we have the list of target names, and that's basically the species names here. So the classification, the numbers are set up so that you can, they're basically the index in the list of the target names. Yeah, so also, this is just another aside about how Scikit-Learn works. When you load these built-in data sets, they'll be saved onto your disk in this location. If you run get data home, it shows you the default location where that data is being stored, and that'll all be done in the background when you type fetch underscore whatever the data set is. So this is what I was trying to show earlier. If you do data sets from Scikit-Learn, import datasets dot fetch underscore, and hopefully if this, I don't know why this isn't working right now. There we go. Yeah, so if you run import datasets, then do datasets.fetch underscore and type tab, it will show you what sort of datasets are in there that you can play around with. And some of these are pretty fun, like the Olivetti faces. That's a database of facial images, and you can practice basically identifying people in images. And there are some good tutorials online for how to do that, but we're not going to do that right now. Okay, so just as another example, this is a fun one, the digits data. We're gonna use the load digits functionality to load this set of basically images of handwritten digits. If we take a look at this right here, looking at the number of samples and the number of features in the digits data set, we can see that we have 1,700 or about 1,800 samples, so about 1,800 images of digits, and each one has 64 features. So you might wonder what those features are in this shape, in this case. And we can, just to look at the first example here, this is what the features look like. It's just a series of 64 numbers. And the target is the number 0 through 9. So we're essentially looking at these samples that each have 64 features that represent a digit. And then the classification, the label is the number 0 through 9 that it's supposed to represent. So to show you what these features are here, you can run pylab inline. This percent here, this is a magic command in IPython. So it's something, it indicates that it's something that's not available in the normal Python interpreter, but it's something that had been added in IPython for convenience. And what I'm doing here, we'll see this a lot through the tutorial. When I run pylab inline, that's saying that all plots I want to appear inside the notebook rather than popping up a new window. So it'll just make things more convenient. I should also say, I forgot to mention this earlier, as we go along, be sure to, within each box that we go through, be sure to press Shift-Enter to actually run the code. Because if you don't run it earlier, then later on there might be variables that are undefined. So as we step through this, try to keep up and press Shift-Enter. So what I'm going to do right here is, this is just a quick code that'll show the digits. And what we're doing is we're cycling through the first 100 of these samples, and we're going to add a little subplot to our plot. And then we're going to take the ith sample and reshape it into an 8x8 array, and then show that as an image. And this will show you what the digits data set is. And it takes just a second because it's got to compute all that stuff. Oh, I'm wondering if it's, oh, there we go. So the digits data set is a set of pictures, and we have the labels that go with them there. So these are 8x8 pixel images that show some handwritten digits. So this just gives you an idea of how you could, if you're looking at images, this is how you would break up an image to be readable into Scikit-Learn for machine learning. You're basically taking each pixel as a feature. So if you have 8x8 pixels, then that's 8 times 8, which is 64 features. And so these digits, even though this is where it can get sometimes confusing, each sample is a two-dimensional array, but you flatten that array into basically a 64 element vector, and then you stack all those on top of each other so that this digits data set becomes 1,800 samples by 64 features. So some of the art in machine learning is sometimes can be figuring out what the features are that you're trying to look at. And for example, in some astronomy situations, we've measured thousands and thousands of features of a data set. And it might be that all those are useful, but it might be that you want to select some of them rather than others. And it really depends on the algorithm you're running, and it depends on what your goal is in doing the learning problem. So any questions about about Scikit-Learn's data representation at this point? The fetching data, the displaying data? Yeah?
I never got the data sets dot fetch underscore the module object has no attribute fetch.
Oh, really?
Well,
Oh, okay.
it doesn't have exactly that, but that's just the prefix of a bunch of functions in the module.
Yeah, so
Your data sets.
Yeah, or IPython, if you hit tab, IPython will pop up a little window that shows you all the
Here we go. Yes, yes.
yeah. Yeah, so that's a tab completion rather than execution. Thanks. Any other questions right now before we move on to the next part? Yeah.
We're kind of talking here about setting up the kind of truth data set.
Well, we're talking about setting up any data set. You can, in this case, this is the truth data set because we have the labels for each one. We know that this is a 0. But we'll also have, we also might have unknown samples, but we just need to make sure we break them up the same way. So if you have an unknown sample, in this case, you would need to run some sort of algorithm to find the digit on the page, to break it up into an 8x8 image, and then that's your set of features. Because let's say you have, if you have this as your training sample, if you have this set of images that's 64 pixels, and you have some more digits that you want to classify that are maybe 144 pixels or 12 by 12, then the machine learning task won't really know what to do with that, because how do you compare 64 features to 144 features, right? So you have to make sure all your data is in the same format. And in this case, this is the training set, but it could be the unknown set if it just didn't have these labels. If we just either forget that we know them or if we don't know them. And we'll see some examples of that later. Does that answer your question, man?
Yeah.
Good, thanks. All right, so let's close this notebook. It'll ask you if you want to stay on the page. That's just whether you want to save all the changes that you've done. I don't want to save the changes, so I'm going to leave the page here. And we'll go back to here. So that was actually just a bit of an aside about data sets and how they work within Scikit-Learn. So I find that when there's a new algorithm in Scikit-Learn that I want to try, when someone's submitted something in a pull request and that sort of thing, I can go back to one of these data sets that's available, like the irises or like the digits, and just try it out, see how it works, see how it compares to things I've used before. And it's a really nice way to do that. I should also say, as we're looking into this, if you go to www.scikit-learn.org, this is the Scikit-Learn documentation, and there are a lot of examples here as well that use these built-in data sets. So, for example, recognizing handwritten digits. This is similar to what we just did. They're looking at the exact same data set, but it just gives you an example of how you would actually go about classifying this data set. And all sorts of other things here. There are tons of examples that you can peruse through. And I've found that whenever there's something that I need to do with my data, I can just go to this examples page. It's basically that top tab at scikit-learn.org. Go to this examples page and just look through and see what sort of things are available and if there's anything that matches the type of problem that I want to do. So that can be really useful. But let's go back. So where are we? So we're looking at general concepts. Okay, so Matt's question earlier touched on this. Here we talked about the training set and the test set. And that goes into the different classes of machine learning. So we're going to talk here about supervised learning, the differences between supervised learning, unsupervised learning, and how that affects the Scikit-Learn syntax. So basically, the two classes are, if supervised learning is the case where you have a set of objects where you know the true value, you know the true label, and then you have another set of objects where you don't know the true label and you want to figure out what the label is for that unknown set. So for example, with the digits we were looking at before, you might have a set of handwritten digits where you know it's the 1, 2, 3, it's been identified by a human, and you might have a few thousand of those. But then you might have maybe a billion other handwritten digits where no human has time to go through and label each of those. So this is a supervised learning problem because you're telling the algorithm what the labels are for a training set, and you want it to predict the labels for another set. One example we use in astronomy is we know that certain objects are stars or quasars or galaxies, but then we have this big survey that's taking pictures of large swaths of the sky, and we want to identify the objects that we see in those other pictures as stars, galaxies, and quasars without the astronomers or grad students having to go through image by image and identify them. So basically, machine learning is trying to obviate the need for grad students. And it really has changed the way astronomy is done. I could get excited and talk about that, but I won't.
This might be jumping ahead, but I'm wondering if it's possible to have a supervised learning, but then have it tuned after that. So in the example you just gave, say, it gives candidates to the grad students of like, I think this is a quasar, would you verify this? And then they can learn from further human interactions.
Yeah, that's a good question. He was asking if there's a way to do supervised learning, but then to tune it later on. basically give feedback when it gives response, check whether its responses are correct, and then from that retrain the model a little bit and make it a little bit better. And there's certainly ways to do that. It's not part of the basic paradigm, but it's once we delve into the mechanics of how this is done, you'll see that it can be done. And there's some models that would be called online models that can actually be updated incrementally, and other models it would be better just to retrain the whole thing from scratch with your new information. Does that help?
Yeah.
Okay. So supervised learning, think you have a bunch of unknown objects and you want to label them or you want to classify them. So an unsupervised learning task is a little bit different. In this case, we don't have labels that we're trying to find about objects, but we might say we have a bunch of samples, a bunch of things that we've measured, and we want to know the relationship between them. We don't really know. So for example, with the digits, we're the supervised learning task, we're trying to label them 0, 1, 2, 3, 4. But let's say you come across a culture that has a different writing system, and you have no way to make sense about what these digits are, and you're wondering if you can classify the different chicken scratches that you're seeing. Not classify, but if you can cluster those different chicken scratches you're seeing and saying these are all similar and these are all similar, so they must indicate a different character. That would be an unsupervised learning problem. So an example in astronomy that we use a lot is dimensionality reduction. So for example, we'll see later that sometimes we have thousands and thousands of observations of each object. And it's hard for an individual to make sense of 1,000 observations. If you have 2 observations, you can plot it in a nice X by Y scatter plot, right? 3 observations, you might be able to do a 3D plot and do some cool graphics. But how do you plot a 1,000-dimensional point? I don't think I could draw a 4-dimensional axis, let alone a 1,000-dimensional axis. So in that case, unsupervised learning can be useful because it will allow you to choose which of those 1,000 features are most important and just plot the important ones. So it allows you to visualize the data set. Another thing we do often in astronomy is clustering. So you have observations of a bunch of objects and you want to say which ones are similar to others. And those can all be useful. So that's unsupervised learning. Does that make sense, the distinction between supervised and unsupervised? Basically, supervised means labels that you're trying to predict. Unsupervised means relationships that you're trying to predict. And sometimes the distinction between the two is kind of difficult to figure out. Yeah.
So supervised learning, since you have a training set, you can actually go and measure your error. How do you measure your error when it's complex?
It's a great question. He asked. He said in supervised learning you have a training set so you can go and you can measure your error, but how do you measure your error in unsupervised learning? And that's a good question. Unsupervised learning tends to be a little more hand-wavy than supervised learning. Like you said, in a classification or regression and supervised, you can measure error and kind of say how well you've done. But in unsupervised learning, it tends to be more for just data exploration. Yeah.
If you trained on several subsamples and then went to see how similar the models were, and the models are similar to each other, then probably that's a pretty good one. If they're all over the place,
yeah, that's a good point. You could train on different subsamples and see how similar your models are. That'd be a way to check. Another way you could check is, say, if we go back up to this up here, if you're doing a clustering routine, you could put in this 2-dimensional data set without actually giving it information about the labels, and then see how close your unsupervised learning gets to actually identifying the correct clusters.
But there's no quantitative way to measure it? Because, for example, here you have a support vector machine learning data set.
Yeah.
How can I judge the quality? How can I say, well, this is a good fit because it puts a mapping into different states?
Yeah, it's a good question about how to quantitatively generate. Yeah.
If your model has probabilistic semantics, find the likelihood function, you can measure the likelihood of unseen data. And that's a way of judging how it's state. If the likelihood of the unseen data is much, much lower, then you know that your unsupervised learning method is over that. Yeah, the most useful
That's a good point. I think it's worth repeating. David said that if you have an unsupervised model that gives you a probabilistic framework, and we'll actually see an example of one of those later, then you can ask about the probability of unseen data points. Is that what you said?
It gets nice, but yeah.
Yeah. So I think the answer is beyond the scope of this introduction. Yeah.
It gets into like philosophy of science. So.
Philosophy of science. That'll be the next tutorial. Yeah. Excellent. Thanks for all that feedback, everyone. So where were we? We were talking about supervised and unsupervised learning, predicting classifications versus predicting relationships. And if you want to visualize, actually. Let's look at this right here. In the Scikit-Learn syntax, we have models or estimators that you train, and the syntax that's used in Scikit-Learn is model.fit, and this fit method is available in both supervised and unsupervised estimators. So for supervised estimators, you're calling fit xy. And that X is the data and the Y is the labels. And for unsupervised learning, you just fit X because there are no labels there. And to go on, when you're looking at supervised estimators, the predict function is the one that actually says, given a new set of observations that doesn't have labels, if you call predict X new, then that will return the Y value that's associated with that new set of features. And what David was talking about a little bit, this predict prob A, this is for some models that have probabilistic interpretations. Actually, this isn't exactly what you were talking about. Some models have probabilistic interpretations. So the predict prob A would say something like, you have a 40% chance of being a 1 and a 60% chance of being a 2, but I can't really tell the difference between the two. So those can be pretty useful as well because it gives you a measurement of how uncertain the prediction is. In unsupervised estimators, there's no reason to have a predict method, right? Because you're not predicting any classification, you're not predicting any label. So the methods that unsupervised learners use is transform. So this would say if you fit one set of data X, then the model.transform would, when you call that on X new, it gives you maybe the equivalent low dimensional representation, or it gives you the equivalent cluster number that each data point lies in, something like that. It depends on the exact nature of the method. And there's also this nice thing called fit transform, which basically fits X and then transforms X all in one. And sometimes that can be a lot more efficient than calling fit and then calling transform next. So just we're going to reiterate this a lot because I want to make sure it sinks in. But this is a visualization of how a supervised learning model would work. So you have your training text, your documents, your images, your features, and you do something to turn them into a feature vector. So this is a n samples by n features matrix. And you also have your labels that go with each object. That goes into this big circle machine learning algorithm that does something and then spits out a predictive model. And then you put in a new document, extract the feature vector the same way you did from the original stuff, stick that into the predictive model, and then you get an expected label out. So just to show you visually what each of these operations is in Scikit-Learn, we have vectorizer things that can basically predict labels from inputs. And the vectorizers are kind of similar to an unsupervised learning model. You're basically taking one type of data and then changing it into a uniform representation. You call the fit method on the data and the labels, and that gives you, stick that into your algorithm, and that gives you your predictive model. The xnew, you use the same transform to get the feature vector, and then predict xnew gives you ynew, which is your set of labels. So hopefully I'm not going too slow or too fast. Most likely I'm going too slow and too fast at the same time, since the room is so full of people. But are there any questions at this point before we move on to the more meaty stuff? Yeah.
The model object, is that the data set or? Okay.
No, I wasn't nodding affirmative. I was just saying I understand. The model object is not the data set. The model object would be a class that takes the data set as an argument. So that'll be a little more clear later when we do some examples. Yeah, we'll do that. Yeah. Okay. Why don't we move on? Oh, because vec is short for vectorizer. It's there are several different vectorizer classes that will take things like it'll take a text document and turn it into something with nice features that you can run learning algorithms on.
There's a few that are built in.
Yeah, there's a few. I'm actually not going to talk much about those, but if you go to the main scikit-learn.org page and click tutorials, I think. Yeah, it might not be here. Olivier Grizel did a tutorial at PyCon back in the spring that involved a lot of text classification. So I think it's either in here or it's on his own page. But if you search text classification with Scikit-Learn, it'll have some examples of that and how to use vectorizers and things like that. Yeah, so now to get to your question, let's do an example of a classification of this iris data set. What did I just do? There we go. So we'll do some more classification later in the exercises section, but for now let's do this one. If you go, we're going to look at the second notebook. So let me switch tabs. Click on O2 iris classification. And this one, as before, we'll import the data sets, import the load iris thing, and load that data. And this time we'll call our data x and we'll call our targets y, because that's the typical notation that's used in Scikit-Learn. So it'll just make it easier to use. So now, getting to your question, this is the model we're going to use is something called a linear SVC, and this is a support vector machine classifier. So don't worry too much about that. If you want to read the details on it, there's a bit in the Scikit-Learn documentation about what that actually means. So we're going to import linear SVC. And when you import a new model, you don't really know what to do with it all the time. So the thing you can do is type linear SVC question mark and then execute that. And this is just an IPython command. It doesn't work in the regular Python interpreter. And that'll give you this nice thing about its documentation here. So this is basically the doc string from the function. So it's linear support vector classification. And the parameters it takes are listed here, and this will be different for every estimator. And these parameters are these are what we would call hyperparameters. So they're things that they're parameters that you set from the beginning, and you say this is the kind of model I want to fit. And then when you call that fit function later, it estimates some things within that model. And some of you might be thinking, well, how do you choose those hyperparameters? How do you decide what kind of model you want to fit? And we'll get into that later. That's something called cross-validation, which is important, but we're not going to deal with it right here. So for this simple example, we're just going to use an L2 loss function, and then everything else is going to be default. So now we have CLF right there. So let me minimize this. So this, your question earlier on what the model is, this CLF, this classifier, I did CLF for short. That's the model that we call everything on. So if we take a look at what this is, the CLF is a linear support vector classifier. It has all these are all the hyperparameters, or the metaparameters, and that'll show you what it is. So remember now that the X and the Y are from our iris data set, right? So X is the features of the iris data set, Y is the labels of the iris data set. And if we call clf.fit XY, then that fits the model. So what's going on here when we call fit is there are a number of parameters that are determined that describe the model. And these are different than the hyperparameters that we put in the beginning. This kind of tells you what sort of model you're fitting. And this, once you do this actually fits the model to the data. So it's a fine distinction there. So in Scikit-Learn, another way to say this is that this is, when we call fit XY, this is learning some sort of parameters from the data. It's learning the interior parameters. And the parameters for the model that are learned when you call this fit method have a trailing underscore in Scikit-Learn. And in this case, the parameters that are learned by calling fit are the coefficients, which is just a bunch of numbers, and the intercept, which is just a bunch of numbers. Right? So this might not mean much to you looking at this, but you can think about this as it's similar to fitting a line to a data set, right? If you have a bunch of points and you want to do linear regression and say what's the best fit line there, the model that you have is parameterized by a slope and an intercept, right? So it's just a couple numbers that tell you what your model is once you've specified that it's a line. And that's a similar thing that's going on here, except it's a little more complicated than just a line and an intercept. But it's actually the multidimensional generalization of a slope and an intercept. And that's what's being fit right here. Does that make sense? Yeah.
Every time you refit the data, your coefficients change. Is there any benefit to going over that again and again, checking the variance?
Oh, you said in this case, if you refit it? Yeah, this one, whoops, what did I do wrong? I need to fit. Yeah, so if you fit, it changes just a little bit. Yeah, the reason is that this is an iterative method, so it's basically saying this tolerance right here is telling it what precision do I care about, right? So we should see if we call this, if we fit again and then look at the coefficients again, it shouldn't change on a level greater than that tolerance right there. So there are two ways. Yes, you could go and fit over and over, call the fit method over and over, but actually the better way to do that is just to adjust the tolerance to what you want it to be. And that's internally, that's the same as fitting it over and over until it gets to a certain point. Does that make sense?
Yes.
Yeah. Yeah.
Are these models, so is there a way to train these models online fashion? Can you just add new data?
Some models have.
All right, so the models which online training is appropriate, right?
Yeah. So certain models, he was asking about online learning. So certain models you can train, or are set up to train things online, which means basically you feed it one point and then a few seconds later you feed it another point. And this is good for situations where you have a data stream coming in. And that's a whole subsection of machine learning, of the field of machine learning is online models. Scikit-Learn at this point doesn't have a lot of models that are well set up for online learning. And David, are there any that you know of that are good examples of that?
Offhand, no.
Yeah.
We
I
had
don't-
a summer code student working on a multi-layer perceptron, but
Yeah.
kind of bailed.
Yeah.
Actually, to work for Google, but
Oh, that's right. So yeah, online learning is a big component that's right now missing from Scikit-Learn, and I think that's one of the reasons that the development team is hesitant to go to a version 1.0, because we'd like to have a good online learning interface and several examples of that before we go to version 1.0. So good question. Okay, so we've looked at the coefficient and the intercept, which is basically a generalized slope and intercept of a line fit to the data. And now what we can do is we can define a new point. So let's say we go out and we find a new iris in the field, and we measure its sepal length, and we measure its petal length and all that, and we can predict what it is, and it says, oh, it's type 0. So if we want to remember clf.target, iris.target names. So the 0 is the setosa. So we've gone ahead and we've classified the new iris that we found. So a simple example, but that's the core of what we're doing with ever more and more complicated data sets. So there are other classifiers available, and I just want to give each of you a chance to work with it right now. So we're going to do from Scikit-Learn import linear model, and then you can type again linear underscore model dot, and then rather than pressing Shift Enter right here, just type tab, and that'll give you a tab completion and show you what all the linear models that are in there. Another thing about Scikit-Learn's syntax is that all the models are classes which start with a capital letter, and there are other things that are kind of like convenience routines and other things that have a lowercase letter. So when you're looking at the list of things, just look at the ones with the capital letters are what you want to look at as models. So here I want to stop talking at you and give you a chance to play around with it. And I have several suggestions of different models that you might use, different classifiers. There are a lot of things in there that aren't classifiers, they're regressors, but we'll get to that in a second. So choose one or two from this list and import it, figure out what the hyperparameters are, and try a fit on the same stuff as above. And I kind of walk you through this right now. So I'll give you about 5 minutes to look at that and see what you can do. And I'll be walking around to answer questions if you have them. So I'm going to really quick run through just a quick example of this. Hopefully you had some time to play around with it. So I'm going to do logistic regression, and I'm going to do CLF2 equals logistic regression. I'll just call the default parameters. And then I'll do CLF2.fit XY. So that's learning the model. And then just because I'm curious, I'm going to do CLF2.tab and see what's in there. So there's something called class weight, which doesn't have anything. Class weight label. Oops. So I know there's something in here that's been fit already. Oh, raw coefficient. That's probably the one that we want. Yeah. So there's the array that describes the model interior to it. And just because I want to, I'll do predict x new. And it found the same label as before. So qualitatively, at least, this model is doing what we think it should. Did everyone, are there any questions? Everyone have a chance to see how that works and how the flow of the models work there?
Could you
What's that?
Could you just iterate over all of your linear models and see what the same interface is like?
Yeah, I guess you could do something like that if you wanted to.
Just compare it?
Yeah, you could compare all of them. That might be worth doing. It'd be interesting. Yeah.
How are you using logistic regression to figure something with 3 values?
That's a good question. I think there's something going on in the background, and I'm not familiar with it enough to say what it is right now. But if you look at the Scikit-Learn documentation, it'll have some information on that. It might be doing a one versus all, a collection of one versus all, or something like that. I don't know.
I think it's 1 versus 1. One versus one. In some, it's in the linear. Okay.
So something a little linear. Yeah. For those of you who aren't in machine learning, he was asking how I was using logistic regression to do 3 different categories, because usually logistic regression is just drawing a dividing line between 2 categories. So you have to do some tricks to use a single dividing line to learn about 3 or 4 different things. But there are ways to do it that are done in Scikit-Learn. So again, we can. We talked a little bit earlier about probabilistic prediction, and I want to show you that real quick because it can be pretty interesting. So if we do as above and import logistic regression, call this classifier to fit xy, and then call predicts prob a x new. What this gives us is a probability that what the model thinks this new thing is. So what it basically says is it's a 90% probability of being the first species, about a 9% probability of being the second species, and a negligible probability that it's the third species. So this is kind of it's probability in a Bayesian sense. For those of you who've done statistics, it's probability about our state of knowledge about this this new object. And again, if you don't care about probabilities, you can just do predict, and it'll basically internally what it's doing is it's saying which of these probabilities is the highest, and I'll give you that result. Okay, so that's classification. That's the first part of supervised learning. Let's close that, leave page, and go back here. So a lot of this stuff below here on the web page is basically what we just did in that notebook. So we'll skip through all of that. And we also talked about several different classifiers that are available. So just as this is kind of a list of some of the things that you might use classification for. You could classify email as spam or normal or priority. You could identify the language of a text document. A lot of this stuff is text-based things because that's pretty important these days. You can look at face verification in pictures and say who it is. You can look at speaker verification in voice recordings. My voice is my passport, verify me. You can look at astronomical sources, things like that. I hope some of you guys got that sneakers reference. Sometimes I just do that and see who listens. Yeah, so the other sort of supervised learning task that we'll see is regression. And the difference between classification and regression is that in classification you're learning distinct labels, you know, this or that, 0, 1, or 2, star or galaxy. In regression you're learning something that's a continuous label. So for example, in astronomy we might want to know the distance to a galaxy. So we have a training sample of galaxies that we know the distances to based on their observations. And we have another sample that we observe and we ask, what's the distance to this galaxy? We can't say it's this or that, either or. That's a regression problem. So So we'll see an example of that later, but we won't do an example of that now. But there are a number of different regression algorithms that are available in Scikit-Learn, and it's the same sort of thing. You do fit x, y, and then predict x, except this time the y, instead of being zeros and ones, the y value, the label, is a real valued class. So it's a continuous class. So let's move quickly to unsupervised learning now. Here, it's a different flow. You noticed before in this region we had labels, and now what we're doing is we're just doing we vectorize and we call fit into the algorithm to make the model, and then given our new data, we vectorize it, run it through the model, and we get something out. There are no labels in here at all, and what we're getting out is a likelihood and a probabilistic model. It could be a cluster ID. It could be a lower dimensional representation. It's something that's encoding the relationship between the data points. So one thing that I've found very important in my work, in my research in astronomy and astrophysics, is doing dimensionality reduction of data. Because we're looking at these high dimensional data sets where, for example, each galaxy and star that we're looking at has 4,000 characteristics measured by it. And we want to learn something about it, and it's too many characteristics to plot, so we do a dimensionality reduction in order to do that. So this everything in this section will be using the third notebook, the iris dimensionality. So let's go to the notebooks and click on the third notebook here. And you might think this is kind of funny to do a dimensionality reduction on something that only has 4 features, because we might as well, we could just plot all of that, but just it's easier with lower numbers of features to wrap our minds around what's going on. So we'll start on 4 features here, but everything we do here could be easily applied to thousands of dimensions as well. So we'll do the same as above. We'll import the load iris function, get the iris data and the target. And this time we're going to use something called PCA, Principal Component Analysis. And this is probably one of the most common dimensionality reduction techniques that's used. And it's built into Scikit-Learn here, which is nice. So what we've done is I did this all in one line just as a shortcut. We've initialized the estimator. We've said we want 2 components out, and we're going to whiten it, which just means that it's kind of a regularization on the data. And then we also fit X.
Can you comment on the white part? Is that a good thing to do? Because you're rescaling all your dimensions. Is that reasonable? For example, you may have dimensions that can scale. So why would you rescale them?
So he asked if whitening is a good thing to do, because essentially what whiten does is if you have, it's a little more complicated than this, but if you have one dimension where all the values are between 0 and 1, and another dimension where all the values are between 0 and 1,000, then what whiten will do is actually shrink the large dimensions so they're all kind of on the same scale. For those of you who've studied statistics, what it does is it makes the data so it's uncorrelated and has unit variance. And he asked if that's a good thing to do, and the answer is definitely sometimes. So for PCA, for example, it's good to whiten data because PCA is a variance-based estimator. So if you, actually, that's not true. Sometimes. It depends on your data, yeah. It depends on your data and what you want to get out. I'm sorry, I can't be more definitive than that.
There's this guy named David McKay who wrote this book on influences. It's really nice book. He says he refuses to use PCA because he doesn't believe in whitening data. He's a fairly influential person, so I was curious as to why.
Interesting. So he refuses to use PCA because
He even mentioned his book is really famous.
because he doesn't believe in whitening data.
Yeah, so I was curious as to why.
Interesting. Yeah, this guy. I'm not sure. I personally have found in the data sets I work with, I've found PCA to be really useful, and whitening hasn't been a problem. But I could imagine that there would be data sets where it would ruin everything that you have as well. So there's probably not a good cut and dry answer on that. But so maybe I should put an aside here. Beware of this whiten. Be careful of what you're doing. And actually, later on when we do our exercises, we'll experiment of using whitening and not using whitening, and see what the effect is. Yeah.
In response to that, I mean, a lot of the iterative algorithms converge a lot faster if you whiten it.
Oh, interesting. So a lot of iterative algorithms converge faster if you whiten the data first. That might be a reason for it. So anyway, we've done this fit with whitening, whether or not it's a good idea, and now we can take a look at what the components are in here. And again, it's as it is with all estimators, it's a list of numbers, and unless you know exactly what those numbers mean, it's hard to tell what's going on here. One thing in PCA, this explained variance ratio, all this stuff, if you're curious what's going on, the Scikit-Learn documentation is actually pretty good. So if this normal scikit-learn.org page has some pretty good documentation. We're working on, my personal goal for this, I would like this to be the best machine learning textbook available and have it free and online. But that's kind of bold, so we'll see if we get there. But so the explained variance ratio is, it'll sum to something close to 1. This basically just tells you what percentage of roughly what percentage of the information in the data set you've preserved in your projection. So since we're doing unsupervised learning, let's take this x and let's transform it into the new dimensions. So we'll get xPCA, and just to show you, if we print x.shape and print xPCA.shape, what we've done is we've taken a data set that's initially 150 points in 4 dimensions, and we've projected it down to 150 points in 2 dimensions. So that's what I mean by dimensionality reduction. And you could do this really easily by just taking a slice, right? You could just do x bad equals x colon, comma, colon 2, and print x bad dot shape. That's a perfectly reasonable dimensionality reduction, but all you've done is throw away data, so it's probably not as useful as something like PCA. So this is what PCA is doing. It's reducing the dimensionality. And for those of you who want to look more into PCA, there's some other nice aspects of PCA that allow you to see what's going on in the dimensionality reduction, but we won't go over that right now. So one thing about this PCA projection is that the data has been normalized. So if we do the mean across the 0 axis, we see that the mean is 0. So that means the data have kind of been centered in the plot. The other thing is the components that come out are uncorrelated. So if you do this correlation coefficient with numpy.correlation, correlation, then you can see that they're uncorrelated, meaning they have the correlation matrix is just an identity matrix. So that probably doesn't help visualize what's going on. So let's do a little visualization. We'll call PyLab inline again to make all the figures show up in our inline in our notebook. And then I've just defined this nice convenience function right here will plot a 2-dimensional point, or plot 2 dimensions from the data. So we'll just run that to define the function. And to see what it looks like, let's call that plot PCA2D on the xPCA and with the iris.target and iris.target names. That's just what this function requires. And what we see is this is the PCA projection. So we've taken that 4 dimensions and we've projected it down to 2 in a way that most of the most of the information is still within those 2 dimensions. And this is what it looks like. And the thing to notice here is that in this lower dimensional projection, it's, even though we didn't put any of the label data in there, it actually does a pretty good job of keeping these 2 separated. And I'm just curious, I didn't do this before, but I want to see what happens if we plot our x bad. Yeah, so it's a little bit weird, right? Because the measurements are in units of 0.1 centimeters, so that's kind of gridded like that. And what you can see in our bad projection is the blue and the green are all mixed together, right? So in some sense, we've lost information. But if we go back to our PCA, what PCA has done is it's chosen, without knowing anything about these colors, it's chosen what it thinks is the best representation based on the model. And from that, we can actually see that it's pretty good at this best representation ends up separating these 2 species in a way that the bad plot doesn't. Yeah?
How do you quantitatively judge the bestness of the PCA? There's a way that PCA is also a good weight, but then you have some data sets that are exercising the PCA much worse. Is there a way of quantifying the good PCA? Suppose as a blind person, I can see how would my model tell me the PCA is going to
Well, so you ask if you can quantify the bestness of a PCA, and I guess there are 2 aspects to that. PCA does find the best possible fit given the model that it has. So what PCA is doing is it's looking for axes that maximize the variance, right? So part of the answer to your question is that this is the best projection given those specifications. But I think more what you're asking is whether PCA is a good method to use on this data set, right?
Right. So like, for example, in your exercises, you said exercise 3, so the PCA was bad and some other models. And you're visually showing us the outputs and saying this is better, look and see why. It's still that those why not PCA. How would I know this PCA?
That's a good question. It gets back to something that was asked earlier. How do you quantitatively judge an unsupervised model? And you could do the sorts of things that David suggested, except PCA is not really probabilistic. It's kind of hand wavy, right? I guess.
Look at like tightness of clusters or something.
Yeah. Okay.
The things mixed together, because if you do PCA and it worked out really well, you've got your communities or your plots really separated.
Yeah.
And if it didn't work out that well, they're all bunched together.
Yeah.
What R does is basically just the percentage of the variance of the first 2 components compared as a ratio to the variance overall. So if you got a lot of data reduction, that means the first 2 components will handle the majority of the variance. So you know you've got a good.
That's a good point. Yeah.
If it's spread out, that means that no matter what PCA does, it doesn't help.
So just what the variance curve, or just your curve, you're saying actually what it
Yeah.
Right. So you just pick a number like 0.9 or something like that, and you say you don't want more than 6 components. And so if the first 6 components capture more than 90% of the variance, then you've got a good model.
On these exercises, that has a really good rates, they can see exactly.
So that's a good point. I should just show what they were talking about here. So let's say we do a PCA with 4 components. So we're basically projecting from 4 dimensions to 4 dimensions, which sounds weird, but it's like a rotation of the data, right? So we do that real quick. Then we have this thing called explained variance ratio, and the sum of that is 1.0. So the explained variance ratio tells you how good each component is in offering a projection. So if we plot real quick the explained variance ratio, let's just do it. Explained variance ratio. Then we'll see something that looks like this. So a good PCA fit will have a lot of variance in the first few components and then not much variance down here. What this tells you is that basically once you've looked at the first 3 components, this 4th component gives you almost no added information. But if this curve were something like, if it were more flat so that the last component had something like 0.2 of the variance or closer to 0.25 of the variance, that would tell you that PCA is not helping you much at all. So does that help? That's what you were saying, right?
So for your quasars and stars question, when we plot this
Well, yeah, we can get to that later, but the quasars and stars require about 12 PCA components in order to explain 95% of the variance. So
So then why would you have, why don't you just use 12 nodes as opposed to using?
because I can't draw a 12-dimensional plot. You know? So it's trying to find a way to represent the data. It's in a lot of ways it's a way to visualize the data without losing too much information. So, but I agree when we get to that we can talk about it. But it's locally linear embedding is a bit suspicious because you don't really know what you're looking for, and you don't really know how well you've done once you've done it. So,
this PCA method, is it doing the final step of doing a an orthogonal transformation?
Yeah.
Right before, okay, because I know some tools, they don't do that. And they give you back, well, it might be just because they're calling just SVD in general, and then you have to call the EOF on that after that. But, okay, so PCA here is doing the final orthogonal transformation too.
Yeah, if I understand your question, I think the answer is yes. Okay, so that's, I should, we'll skip this exercise because it's not really anything extra, but basically if you can do everything we did above with PCA, except do it with randomized PCA, and this is something that does an iterative solution and is a lot faster for when you have lots of data or lots of dimensions, and we'll get a chance to look at that later, but I don't want to run out of time. So let's close this and leave page, go back to, here we are, yeah. So all this stuff is just what we did in the notebook right here. So the last thing before, we're going to break in about 15 minutes for do a coffee break, snack break. The last thing I want to do is look at clustering. And I thought no, we do have clustering here. Yeah, the fourth notebook you can pop open for clustering. So we're going to look at the iris data set again, and this is another class of unsupervised learning tasks. So rather than dimensionality reduction, this is the case where we're looking for clusters of data without knowing what their labels are. So again, we'll load the inline PyLab, and I just did a lot of stuff. This is all taken from the last notebook. This is exactly the stuff we did before. Loading the iris, computing the PCA, defining the plot 2D function. And now what we're going to do is we're going to do a clustering thing. We're going to use something called k-means. And what k-means does is it says we say, hey, I think we have 3 clusters here. And then it looks for clusters that minimize basically the distance of each point to its respective cluster center. And it's something that works iteratively. It pops down some guesses of where the clusters are and then says this isn't very good and moves them a little bit, and moves them a little bit, and moves until it finds the place you want them to be. So we're going to import from cluster k-means. We're going to define a random number generator. And we're going to use 42 because that's everyone's favorite number. And we'll define this k-means model the same way we did before. It's we call k-means, we give it some parameters, n clusters equals 3, and we're going to give it this random number generator just so we can have repeatability. Because otherwise it'll use some seed based on the clock time or something. So we create that model right there, and then we call fit, and we'll fit first on the projected data just so we can see what's going on. So we fit on XPCA. And then
Error on n clusters.
oh really? So that must be, yeah. So I'm using bleeding edge scikit-learn. So if you're using an older scikit-learn version, use k equals 3 rather than unclusters equals 3. So now let's take a look at where the cluster centers are. We'll round it to the second decimal just so it doesn't look huge. So this says that we have these 3 clusters in 2 dimensions, and this just gives the XY location of each cluster on our PCA plot. And we can look at the labels. This basically tells you, well, let's look at all of them, even though there's a lot. This tells you what the k-means has decided the best label is for each point. So what we can do is now we plot 2D, the XPCA, we can plot the labels as the colors, and we'll just call them C0, C1, C2. And next to it, we'll do the same plot we did before, which was with the true labels. So just to see what's going on. So the top plot shows you what the k-means clustering has done. The bottom plot shows you the true results. So some coffee or whatever they need. Just going back real quick to this exercise that we left off with. If you fit the classifier on the full data set rather than the PCA, and then plot the labels, remember this is our first set of labels where it didn't match the true values very well. But using the full data set got a little bit closer to the true values, right? So what's going on here is the PCA projection actually throws away some information to get that 2-dimensional projection. And it tries to do a good job of not throwing away important information, but here we can see that we actually did lose some information by doing that projection. And that information that was lost was useful for k-means to do a better clustering of the data. So this is just kind of by way of warning. If possible, you don't want to throw away data for your classification tasks because classifiers in general work better when you have more data, but we'll get to the details of that later. Any questions on that? Yeah. We could. That's something you could check out on your own. I'm not gonna do that right now. But you know, you could import dbScan and then use the question mark to see what characteristics it takes. But I don't want to fumble around in front of everybody and do that. It's fun to explore on your own though. So I'm gonna leave this page and we'll go back here. So that's the clustering section, and there are a number of different clustering models that and other unsupervised models that you can learn. K-means, mean shift, dbScan, locally linear embedding, and then the rest of these are kind of dimensionality reduction models. So let's go into this real quick. This is kind of an interesting thing for an interesting exercise for doing linearly separable data. And if you have the GitHub repository installed, you can find this in examples/svm-GUI. Otherwise, you can click on this little here button right there, and that will bring you to the code. And if you click on svm-gui.py, you can then download the file. But if we run that, Python doc slash, oops, not doc, examples/svm-gui.py, this gives you just a little graphical interface to try out some of these classification models. And this is kind of fun. We won't spend too much time on it, but a left mouse button gives you white points, right mouse button gives you black points, and then you can try a linear fit, and you get this nice separating line there. You can plot it as a surface if you'd like. And then if you start adding other things, like let's say some black points over here and some black points over there, all of a sudden your model doesn't look so good anymore, right? You have this dividing line that's not really doing anything. But you can change to RBF, that stands for radial basis functions. This is just a way to make your fit nonlinear. And that does a little better job of doing this. So this is something that, that can be interesting to play around with. One thing that's interesting is a simple problem is the XOR problem, which is mentioned on the page, where you basically do 4 points and you have 2 black ones in the corners and 2 white ones in opposite corners. And if you try to do a linear fit to this, there's no way you can get this to fit linearly, because it's not a linear problem, right? So nonlinear in this case means that you can't find a single line that will separate these examples. But if you do an RBF, then you see that it's pretty straightforward, or a polynomial kernel. That's a little weird, but I don't know what's going on. But if you do an RBF, radial basis function kernel, you see that you can do some things with these with nonlinear separators that you can't do with linear separators. So I'm not going to spend too much time on that right now, but it's just a kind of a fun thing that you can play around with, maybe on your own time. And there's some exercises listed here that might be interesting if you want to come back to those. But more importantly, I want to go down to this section on hyperparameters and cross-validation. So we talked earlier about how models, when you instantiate a model, you give it these hyperparameters, which are basically saying this is the type of model you're fitting. An example of that might be in a polynomial fit. If you take this data set, these two, this is just kind of a house size versus price data set that I made up. A lot of this actually comes from Andrew Ng's machine learning tutorial. It's a video tutorial through Stanford that's really, really interesting. If you ever get a chance to take that online class, it's really good. But basically, if you have this house price data and you're trying to fit a model to these house prices, this is a regression model. We're going to use a polynomial model here, and the hyperparameters in polynomial are saying what degree polynomial we're fitting to it. So,
just out of curiosity,
yeah.
Why hyperparameter versus parameter?
Because in general, a parameter is something that is fit from the data, and a hyperparameter is something that you specify before fitting your parameters. Yeah. So the hyperparameter here is, you're saying it's a first degree polynomial, so it's linear. And that doesn't fit the data so well, right? So you might say, okay, that doesn't fit the data well. Let's try to do a 6th degree polynomial. And we can see that fits the data really well, right? It goes through every single point. We've done a really good job of fitting our training set. And this is an example of what we call overfitting, right? Because our training set is fit really well. We've done a perfect job of it. But if we added more points in there, it's pretty clear that we're not actually fitting what we think we're fitting, right? So somewhere in between is probably better, and this is what d equals 2 looks like. And that's closer to the relationship that we look for. They're probably not perfect as well. So this is just by way of warning. You need to make sure that you're setting those parameters correctly. And sometimes if you're just evaluating how well your model does on the input, you can end up in an overfitting situation like this. So we'll talk about some solutions to this in the next example. But basically, the solution is to have a training set and a test set. So you have a training set that you know the labels for, and you build the model from that. And you also have a test set that you know the labels for, and you test the model on that. But the test set doesn't go into the training. I'm trying to figure out if I want to do this right now or just go into the next. Yeah, why don't we go, I'm going to skip this example right here, and we'll just go into the next example, which is a little bit more in depth. Because I'm tired of irises. I don't know about you guys. I think we're finished with those. So let's go to the next one. And this section 3, practical advice. This is all about cross-validation and choosing your hyperparameters in a way that avoids underfitting and avoids overfitting. And in my opinion, this is probably the most important aspect of machine learning. So if you want to go to sleep later, but pay attention for this part, because this is something that I think a lot of machine learning courses don't teach quite enough, because it's not enough just to be able to run the algorithms. You need to be able to know what to do with them. So by the end of this section, I want to make sure you guys know what bias and variance are, and related vocabulary, what overfitting and underfitting is. And basically, as a sneak preview, something that overfits. Something that underfits has high bias, and something that overfits has high variance. And we'll talk about why that is. And we'll also go look at some practical examples of how to tell if your data set is high bias or high variance, etc. So there's a lot of stuff on this page, but pretty much everything from this page is duplicated in this number 6 notebook. So 6 learning curves notebook. So let's click into there and take a look. So essentially what we're going to do here is we're going to explore some data sets very similar to the ones that I just showed you. We run PyLab inline, and yeah, so we're going to, what I just showed you was the polynomial fit to this data, right? And an easy way to do that, this is outside Scikit-Learn because it's just a nice matrix operation, is to use numpy.polyfit. And so if we create a data set that's x versus y, where x is just some random number and y is the sine of 2 times x, and then we call polyfit and we say we want to fit a first degree polynomial, that's simply a line, right? What we get is a slope and an intercept. And then if we find a new point, and we can use polyval, this is like an evaluation of the polynomial, to predict what the new y value is, and we can see how close that is. Yeah, we can see how close each of these x points are to their corresponding y points. So it's off by about 0.2, something like that in each one. It's easier to see what's going on if we actually plot this. So I have a function here that will import PyLab, define a plot fit function, and then call it on x and y. So this is what we're looking at right here. We basically have a part of a sine wave, and what we've done is we've fit a line to it. And not surprisingly, the results, when we use that to predict a new value, it doesn't work very well, right? Because it's underfitting the data. The model is not complicated enough to fit these data points. So the interesting thing is when you're confronted with a situation like this, when your data is underfit, or when your fit isn't very good, you can imagine doing one of several things. You could think about increasing the number of training points. Maybe you have a more complicated model. You can't see that the line is just not fitting the data well, and you say, well, this isn't working, so clearly I need to go out and I need to make more observations and make sure I have more input into my data. But that wouldn't help here. It doesn't matter how many points on the sine wave you have, a line is never going to fit it, right? So this is one thing that's important. We see this in different fields all the time. Someone, like, for example, stock market prediction. You might think the best way to predict the stock market is just to gather terabytes of data from the past, right? And then we fit a nice line to it and it'll work well, right? No, you have to do something more than just blindly gathering data. So one thing you could do here is you could increase the degree of the polynomial, and that might work, right? And in this case, it certainly would work. But when you have things like we saw before, increasing the degree of the polynomial might not work. The other thing we could do is add more features. In the case of looking at galaxies, you might observe the galaxies through more filters just to get more data that way. And at first glance, it's not always apparent which is the best course of action. And sometimes those courses of action are really expensive, right? So, for example, the question of whether you need more data or more features to make your model better, does that mean you take your telescope some night and you look at a new patch of the sky? Or do you use your telescope and re-observe the same patch of the sky? And it's expensive. You know, a 10-meter telescope costs millions of dollars a year to operate. So that's not a decision you want to make lightly. So so doing this sort of analysis that we're going to do here is important because it will help you in science to allocate your resources correctly to solve the problem that you're interested in solving. So this is all about bias, variance, overfitting, and underfitting. So we're gonna, I have a couple utility routines right here that you just have to press Shift-Enter and run them to define them. So the first one is a test function, and this is just a function that we'll use to fit data. And then computing the error, this is pretty easy. You just do you have a polynomial degree p, and you do a polynomial fit, and then you, actually that's not a polynomial, that's a polynomial fit to data. You do an evaluation of it, and then you get the square root of the mean square difference, RMS difference. So we'll run this code right here. It's a lot, don't worry about looking through it, but that basically just generates the example plot we were looking at before, where we have an underfit, we have something that fits basically pretty well, and then we have an overfit. So I have lots of text here because I'm hoping you guys will go back through and read this and think more about this, because we're just going to kind of storm through it right now, and I think it's really important. But what we're going to do first is we're going to define a data set that we can use to explore this cross-validation. And it's going to be very similar to the one up here, except we'll have a lot more points in it. So let me walk through what we're doing really quick. We're going to randomly sample. Actually, first we're going to say we want 100 training points, 100 cross-validation points, and 50 test points. And we'll go into what each of these mean a little more later, but it's important when you're evaluating a fit that you have these data sets. So we're going to create a random array of x values that has the number of points that has all these points in it, and then we're going to evaluate our test function on each of those x points, and we're going to add an error of plus or minus. Normally distributed with a variance of 1.0. So this will just kind of give us a nice scatter plot of points. We're going to define our training set here, our cross-validation set, slices of the array, and the test set, and then we're going to scatter our training points and our cross-validation points. So take a look. So this is the data we're working on. We have the blue points, which are our training set, and the red points, which are a subdivision of the training set that we'll use for cross-validation. And what I mean by cross-validation is it's kind of it's used to prevent this overfitting right here. If we fit a curve like this on our blue points and then tested it on our red points, it probably wouldn't fit the red points very well, right? Because it's overfit. The red points that fall in between these points here would be off by 1,000, something like that. So the reason we need a cross-validation set is because we want to make sure we're not overfitting. We're not making the model so complicated that it just contorts itself to go through every single training point. Does that make sense so far? Yeah? Okay. So blue points are our training points. Red points are our cross-validation points. So what we're going to do now is plot something called, some people call it a learning curve. So what we're going to do is we're going to try out different polynomial degrees and figure out which one is the best for our data set. So we'll try polynomial degrees between 1 and 20, say, because that's just a good place to start. And we'll compute the training error, we'll compute the cross-validation error, and we'll compute the error on the test set as well. And I'll get into why we need the test set later. So basically, we take the blue points, we fit a curve to the blue points, we ask how close that curve is to the blue points. That's the training error. And then we throw in the red points and say, the model knows nothing about these. We're going to see how close the curve is to those red points, and that's the cross-validation error. Okay? So let's look through this code here. We've defined the degrees to be an array of 1 to 20. We're going to iterate over those degrees. We're going to fit a polynomial to the training data. We're going to compute the training error, and we're going to compute the cross-validation error and store those in the arrays. And then we'll make a figure that will plot the two of them. So let's run this and see what it looks like. So we get a rank warning, right? Because we're fitting this high degree polynomial to a low number of data points. So don't worry about that. It's just saying that the polynomial isn't fitting well when we have d equals 20, things like that. So this is what we get. This is the learning curve, and once again on the x-axis we have the degree of the fit. So how many with a polynomial degree. On the y-axis we have the error, and this is a pretty typical example of what a learning curve might look like as you increase model complexity. So essentially, the degree of the fit is parameterizing the model complexity. How many twists and turns we allow the curve to take, right? So the training error, as you'd expect, as you increase the model complexity, the training error just keeps going down, right? Because more parameters allows us to get ever closer to those points. And if we went up to, if we did a polynomial of degree 100, then we'd end up fitting the data perfectly, right? Because a degree 100 can go through 100 points by definition. So the training error isn't very helpful to tell us how good our model is doing, because it just favors a more complicated model all the time. But the cross-validation error, you can see we have up here, it goes down as we increase the complexity, and then it hits a low point and starts climbing. So this is why cross-validation is important, because what it tells us is that over here in this region, the model is underfitting the data. This is like fitting a line to a straight line to a sine wave. You just can't, the model's not complex enough. So what we would say in that case that the model is biased. So the model is biased and it underfits the data. Those go hand in hand, bias and underfitting.
Do you have a mnemonic for bias and variance? I can never get them straight.
Yeah, not really a mnemonic, but I just think of a biased model as one that'll never work, right? You can't, if your model has high bias, then I don't know.
For me, it's like high bias, it's like it's biased towards the data.
Oh yeah, that's a good point.
I think it's like the model's too pushy. The model itself is biased because you're trying to like say,
Yeah.
this is linear, right?
Yeah.
Shove things towards
Yeah.
linear, so it's a bias.
Yeah.
So what's the
More optimal, is it 3 or 5?
3 or 5
Are these points?
for the degree, or
Oh, I see.
what do you mean?
For the degree of fit.
Oh, okay.
I mean, do you look at really the lowest point
Yeah,
in there,
in
or do
general,
you
you
look
look
at?
at
Well, I don't need. As I increase the degrees, I don't really get much from 3 to 5. Do you look at 3, or is?
Yeah. Usually you take the lowest, you take whatever the best cross-validation error is. And in this case, we've only used a single cross-validation set, and there are other cross-validation strategies that allow you to, this right here, you can see the line wiggles kind of all over, and you don't know exactly where it is. But there are other cross-validation strategies that allow you to zero in even further on what the best is. But in this case, somewhere probably on my plot from 5 to 6 looks pretty good, right? So we're going to go with that for now.
So is 1-to-1 a good ratio for the training versus cross-validation numbers?
It really depends. I did 1-to-1 here. Some people recommend 80%, 20%. I've heard recommendations all across the board. But it really depends on your situation, and we'll see this a little bit later. If you're at a place where you need a lot of data for your model, so 50% of your data isn't enough to train a good model, then it might be better to do like a 90-10% or something like that. It depends on your problem. Okay, so on the left we have biased models that underfit the data, and a biased model has the same bad error for a cross-validation and for the training set. On the right, we have an overfit model that has high variance. And the reason that this is called high variance is you can imagine if you varied these points a little bit, if you moved one of these points just slightly, the entire model would change really appreciably. It'd be a huge change in what the model predicts everywhere.
So let's say you use the cross-validation set with what degree you fit 5. Would you then go back and do a cross-validation set back in the data set to improve the model? Or?
Sometimes you could. It depends on the situation. He was asking about once you figure out the best model, do you throw the cross-validation error data back in to improve it? We'll get to that a little bit later in more detail. So I just wanted to get back to your question about the mnemonic for bias and variance. I know I always think of it as high variance because if you vary these points a little bit, the model will change a lot. If you varied this point, if you shifted this point back and forth a little bit, the model wouldn't change much, right? So we know that overfitting is high variance for that reason. So just some nomenclature. So this is how you recognize a high bias model versus a high variance model, by plotting the complexity. Sometimes the complexity isn't something that you have a continuous scale. So a good way to see what's going on with a model that you can't adjust so much is to just do a cross-validation in a test set, and if the errors are nearby each other, then that means that it's probably underfitting the data, and if the errors are far apart, then it's probably overfitting the data. And you might think, why do we need to do all this when we can just plot stuff like this? This is a lot more intuitive. But imagine trying to do regression in 1,000 dimensions. How do you see how well your plot is doing? And this is the way to do it, the learning curves.
What's the intrinsic error? That's just because you're generating this.
Yeah, the intrinsic error is just we added a spread of about plus or minus 1 to each point. Because this is a tight relationship that we started with, and then we added in our function we added an error of 1.0, and I just plotted that for reference there. So you don't always know the intrinsic error. This is just in our toy set here.
But at a degree of fit of 5, you're actually able to beat the intrinsic error, right?
Yes, that means.
That's not an artifact. That's a real thing.
Well, it means that the intrinsic error it's just kind of a rough estimate rather than truly what's going on, because it's.
You can add a lot of error to these things and yet come up with very accurate predictions. Way.
Yeah. Yeah.
So that's an important and useful finding.
Okay. Yeah. So you can even with that level of error, you can do pretty well. But notice though, this is just about 5% below the error. So, the 0 is way down here. So, yeah. So where are we? Learning curve. So another thing that you might wonder is going back to your question: how does adding new data affect things? Right? Because let's go back to this. If we just had 2 training points, then a line would be a perfect fit to them, right? And adding any more degrees of polynomial wouldn't be a good thing. But as we add more, as we have 3 points, 4 points, 5 points, and more, it's better to have a polynomial. So the number of training points really affects what sort of model you should use as well. And one way to do that is to plot, similar to here, how we plotted the degree of fit versus the error. We can plot instead we can plot the the number of training points versus the error. And there's a little bit of confusion here sometimes. For the training error, we want to evaluate the model on only the data that's been used to fit it. So that's the definition of a training error. If you've trained the model on a certain data set, you want to use just that data set to evaluate the training error. And the cross-validation error is a completely different data set, so you use that whole data set each time. So we're gonna, I just made a function here that will plot the learning curve for some value of d. And d is the degree of polynomial. So we're gonna choose the degree of our polynomial, and for that degree, we're gonna ask what the error does as a function of the number of training points that we have. Does that make sense? Yeah, okay. So, so in this function, we're gonna plot the learning curve. So we'll make a sizes array. We'll have the array of data set sizes from 2 all the way up to our whole training size. And we'll just choose 50 different samples in between. We'll have the training error array and the cross-validation error array. So just as before, we iterate through the sizes. We do a polynomial fit, but we're only training on the data up a certain amount of the data given by the size variable, right? And we compute the cross-validation error, compute the training error, and then we plot the results. So we're gonna define that function, and then right here, let's plot the learning curve for d equals 1. So degree 1 polynomial means we're fitting a line to the data, right? So this is overfit or underfit. This is an underfit model with high bias. It's a biased model. So what we see is we have the training error in the green and the cross-validation error in the blue. So as expected, when there are 2 points, you can fit a line perfectly, right? So the training error is 0 when you're fitting a line to 2 points. But as you add more and more points in this plot, you end up not being able to fit it quite as well. So the cross-validation error, though, when you're fitting a line to these 2 points, you're not doing very well fitting the whole data set. So that's what the cross-validation error is showing you. And as you add more and more points in the training set, you get closer and closer, and eventually the cross-validation and the training error are about the same. So just for reference, if we go back to here, what we're saying is that when a model is underfit, when it's high bias, the cross-validation and training error are the same, right? And we've recovered that situation here. We have it as we add training points, we get to this high bias model. Now the interesting thing here, though, is that remember again, high bias models, the cross-validation and training error are the same. High variance models, they're really spread apart. But what this says is that if our training set size is 10 points, then we have a high variance model even for just a line fit to it. So the difference between bias and variance depends on your training set size. And that goes back to the idea that a line fits 2 points, but a line doesn't fit 100 points. And so this is a way that you can figure out a little bit what's going on with your model. So if we have 100 training points here, and we plot this data set, we can see that we can make this model a lot more complicated without losing without overfitting, right? Because this is kind of the point right here where we transition from overfitting to underfitting. So we can afford to push this out a little bit and make the model more complicated. So let's do that. Let's plot the learning curve with d equals 20 and see what happens. So now we see with d equals 20, we've kind of overshot ourselves, right? Because we're underfitting the data over here, and with 100 points, we haven't quite gotten to the place yet where we've converged. So we're not doing so well here. We need, in this case, we would need more data to fit this model correctly. All right, and in this case, we need a more complicated model to fit the data that we have. So above, we thought around D of 5 or 6 was the right answer. You know, it was good for the amount of data that we had. And this is what the 5 or 6 looks like. So, and what you'll notice here is with D equals 6, we've basically converged to exactly what our, well, within a little bit, we've converged to very close to what our intrinsic error is, modulo the comments over here. So this is just a way to look at your models and say, and figure out how to improve them. Do I improve my model by making it less complex? Do I improve it by making it more complex? Do I improve it by adding training points to it? And in general, so in summary, if your algorithm has high bias, well, let's review that really quick. So a high bias algorithm, if we look at the degree versus the error, high bias means that both the training error and the cross-validation error are the same. The model fits both equally badly, right? So that's a high bias model that underfits the data. And if the model fits the training data really, really well, but any other data point you throw at it isn't fit very well, then that means it's overfitting the data and you have a high variance model, right? So this is how you recognize it on this type of plot, and then on the learning curve plot, you recognize it by these being far apart or close together, right? So if you have a high bias model, what might help, you can add more features. That's kind of a way of making the model more complicated. If you throw more features of each data point at it, then it allows the model to fit each point more. You can use a more sophisticated model. In our case, this was increasing the polynomial degree. You can use fewer samples. I don't know why you'd ever want to do that, but that would help you. You wouldn't be overfitting, or you wouldn't be underfitting anymore. If you reduce the number of points to 2, you're not underfitting anymore, but that's kind of a silly way to solve it. And you can also, there's something called regularization. We're not going to talk about that, but what did I just do? Where did that go? Oh. Yeah, there's something called regularization that if you, that some models in Scikit-Learn have, that basically regularization acts to impose simplicity in the model. So if you decrease the regularization, it makes the model more complicated in some ways. If you have a high variance model, if your training error and your cross-validation error are very disparate, then you want to use fewer features. You could do something like a dimensionality reduction technique, though it may or may not be useful. You definitely use more training samples if you can. That's a good way to make a high variance model better, is to throw it at more data so it can't overfit the data anymore. That'd be, in analogy, that would be like taking the 2 points that you're fitting a curve to and throwing 100 more points in there so the curve is constrained to what your model is. And you could also increase regularization, which is another way of making the model somewhat more complicated. So we just flew through this right here, but hopefully I instilled in you the importance of cross-validation and the importance of thinking about these sorts of things when you're selecting your model. This is the place where machine learning becomes less of a science and more of an art in my mind, because there's not always a best answer. You know, if you see a plot like this, does this mean you have to increase the model complexity? And the answer is definitely maybe, depending on the situation. So any questions about that before we move on to the next section? Yeah.
Does Scikit-Learn have the like k-fold and leaving out kinds of things?
Yeah, it does in import cross-validation and cross-validation dot. We have k-fold cross-validation, bootstrap, leave one out. All sorts of different things, stratified k-fold. So if you want details on all of this, you can again go to the Scikit-Learn website and look at the documentation. So there was a question back there earlier about about if it's best to split your model 50-50 or 60-40 or whatever. And the answer to that is actually it's usually best to use a more sophisticated cross-validation than to just, what we've done right here is, what would we call it? It's a twofold cross-validation. Well, it's not even that. It's half of a twofold cross-validation. So, other questions? Yeah.
If the data has fundamentally changed today from what historically you had, is that high variance?
So he was asking about if the data has changed today from what we had before. So so you're thinking more in an online setting. So, or maybe this could be a situation where, say, okay, I'm thinking about astronomy. If you have a certain telescope where you've observed the training data in one part of the sky, and then maybe you observe the test data with another telescope in another part of the sky. But if those telescopes have different characteristics, then the data sets will be intrinsically different. Is that what you were asking?
Like all of a sudden there's like a new process that's just been discovered for stars that affects everything. And so everything that you've been looking at has fundamentally changed.
Okay.
And you've been looking at it a certain way. I don't know. I'm thinking,
could be if you're thinking about fitting the new data with your old model, like predicting on the new data with your old model, then that would be an example of a biased model, right? Because your old data doesn't match the new data, so the model is intrinsically biased. And that you could correct for that by trying to account for the changes in the data, and that would be
by adding more dimensions.
Yeah, that would be in some sense making the model more complicated to reduce the bias. But that's a good point. You always have to make sure that what you're training on and what you're fitting are the same type of data. If all your training data come from a really old telescope and all your testing data come from a new telescope with different noise characteristics or different response, then you'll end up with a biased model. So that can be difficult sometimes to deal with. Yeah.
You talked about using a more sophisticated cross-validation approach. Are you talking about using like more folds, for example? Or
more folds. So we had one training set and one cross-validation set. Something you could do, you could split your data into 10 different parts, and you train on 9 of them, and then cross-validate with the 10th, and then do that 10 times. So those are some of the more sophisticated cross-validation techniques you can use. Other questions? Okay, let's close this now, and we've now, what time is it? 10:30 about? Yeah, so we've now gone through all the basics, and what we're going to go into now from here is more applications. So let's look first at classification, and I'm not sure. I think especially the exercises towards the end, there's going to be a fair bit that we don't get a chance to go into. So if you're interested in this, it'll be homework for home. But we'll start. Just to give you an outline, the next few sections, we have a section on classification, a section on regression, and then a section on dimensionality reduction. And then after that, there's a page of exercises, and there's essentially one exercise that goes with each of these sections, with the classification, regression, and dimensionality reduction. So I just want to frame the problem for you right here. I'm going to use astronomical data for this example, as promised. So basically, when we look at stuff in the sky, we take the light from each individual star and we split it into its spectrum. You can think of it as very similar to putting a light beam through a prism, and it divides it up into the rainbow, right? But stars have very interesting spectra because the molecules emit and absorb certain wavelengths of light due to the due to their nature. So for example, this black line right here shows a spectrum of a star called Vega, which was used for a long time as a standard. The y-axis gives you the flux, like how much energy is coming, and the x-axis gives you the wavelength, so basically the color. Down here are bluer colors, and up here are redder colors. And this actually goes outside the visible wavelength, so we're going all the way from the ultraviolet on the left to the infrared on the right. So if we have a spectrograph that can take that spectrum and split it all the way up, then we see something like this curve. And these little dips in it are actually due to the absorption from hydrogen. There's cool hydrogen in the atmosphere of the star, and the star emits a nice smooth black body curve, if you're familiar with the physics of that. And that smooth curve passes through that hydrogen, and the hydrogen absorbs certain colors in very narrow bands. So that's what we're looking at with stars and galaxies. But the problem is taking a spectrum like this is very time consuming and very expensive. If you imagine trying to get the light from a single star on the sky and put it through a spectrograph slit and then measure it, that's kind of an expensive process. So what astronomers do instead is they take broadband imaging. So these colored curves are examples of filters that are used. These are the filters from the Sloan Digital Sky Survey. And basically, if you imagine taking all the light that's within this filter profile and then looking at that, that's what we call the U-band measurement. And then we have the G-band measurement, which is all the light which is inside that filter profile, et cetera. So the data underlying is continuous, and we can think of it as thousands and thousands of dimensions, thousands of features for each object. But since we can't get all those thousands of dimensions on lots of stars, we end up getting only 5 features that kind of describe the broad shape of the spectrum. So we're limited by physics and by money in how much data we can get. So as you might imagine, if you look at the spectrum of these stars, if you look at the shape of stars and galaxies and things like that, it's actually very easy to tell what something is just from its spectra. And an astronomer could look at a spectrum and tell you one of 100 categories that it fits into, just depending on what type of object it is. But as you might also imagine, if you only have these 5 colors, it becomes a much more difficult prospect, right? So this is an example of a classification task where basically if you have an astronomer with a spectrum, you can identify the true label, but all you have are these 5 features, and from that you want to use a machine learning algorithm to predict what the labels are for the objects that you didn't have time to get a spectrum. Yeah?
I'm wondering about the shape of each of these, because with the data reduction, you're really just going to have one number of regions, right?
Yeah.
So is this?
Yeah, the shape just tells you how much transmission there is at each point. So the red band at the very center, half of all photons get through, and out at this edge, only 10% of these photons get through, and 0% of these photons get through. Yeah, there's a dip in the eye because there are that's an absorption line in the atmosphere. So these, I can't remember. I think these filters are convolved with the atmospheric response. So
If that were in space, you wouldn't see that.
Yeah, so
Earth-based atmosphere.
Earth-based atmosphere. Yeah. So some of these, I think the I-band is actually designed to suppress the response right there because you just get garbage anyway, because the sky is emitting lines and absorbing lines.
Is that a water line?
It might be a water line, yeah. Matt might be able to answer better. No? Okay. I know he does some of that Sloan stuff. Anyway, so that's the kind of data that we're working with, and you can see why we'd like to just take spectra of everything, but we can't, right? So here's all the math. You can ignore that. So basically, why is this important? So if we want to look at stars and quasars, a star is something that's inside our galaxy, just like our sun, it's floating out there. A quasar is a black hole at the center of a distant galaxy that's 10 million times the mass of our sun, and due to all the gravitational energy is spitting out X-rays and gamma rays and visible light, and it's really, really interesting stuff going on there. But the problem is when you look at the sky, this is a star, and that is a quasar, right? So from the images, you just can't tell, right? You need the spectrum. If you have this spectral data, it's really easy to tell the difference between a star and a quasar. But just from the images, you can't tell. And this, just for reference, this is what a galaxy looks like. So here's a collection of 100 billion or so stars that's a few hundred million light years away. And that's what it looks like. So it's very easy to tell a galaxy from a star just by the morphology, just by the size of it on the sky. But stars and quasars, it gets a little hairy, it gets a little tricky. So we're going to do a star-quasar classification now based on something called naive Bayes. Naive Bayes is one of the most simple probabilistic classifiers that you can use, and it's kind of an interesting example. So we're going to go to the dashboard, and I should say that this example, if we click on classification example there, this one assumes that you have downloaded it assumes that you have the tarball from this little memory stick, or that you have run the Python script to fetch the data. So if anyone hasn't done that, if anyone needs the memory sticks, you can pass those around. Yeah, it'll find it if you're in the notebooks directory. And I have, if you got the tarball the other way, not from the memory stick, there's a fetch data script, but it might take a while. So let me just show you that real quick. If you go to so here's the notebooks directory, right? And if you cd into the data directory, you have something that looks like this. We're going to go into SDSS colors, and the data set is right there. They're NPY files, which are like NumPy compressed files. And if you don't have those, you can do python fetch data.py, and it didn't do anything for me because I already have them. It'll check if they're there. But if everybody does that right now, then the wireless is going to go away. So don't do that. Yeah, so the place where that data is in this directory. And if you're in the notebook directory that I gave you, this should work, hopefully. Otherwise, you can modify that path to where you have the data stored. So we're going to get the training data and the testing data, and we loaded both of those. And this is where I cross my fingers and hope everyone's able to get it. All right, is it all right for you guys who use the memory stick? Yeah? Good. Yeah, I did something right. So let's look at the training data names. So what we have here is, so for historical reasons, I showed you this, sorry, let's go back here. I showed you these filters, there are 5 filters, but for historical reasons and for calibration reasons, astronomers generally take the flux in this and divide it by the flux in that, and take the flux in R and divide it by the flux in G, etc. So, and it's similar to kind of normalizing the data by the brightness. So the names of these are the U minus G, GR, RI, and IZ. That just means the relative flux between those two bands. And then the last one is the redshift. So we can see how much data we have here. Oh yeah, sorry. Train data is what's called a NumPy record array. So it's a way of storing data contiguously, but also with labels. Yeah, in the other room, they're probably going over that right now. So just bear with me on this, and you can look at the details later. But yeah, basically it's a record array, so it's data and names together. So the way you access the data is to use square brackets with the name right here. So the shape of the U minus G data is 505,290. So we have 505,000 training samples. So things have gotten pretty big. But this isn't in the format that we want it. We want it in a number of samples by number of features matrix, right? So we'll construct that right here, and I'm just going to use VStack, the vertical stack thing. So we'll stack the U minus G, G minus R minus I minus Z, and then transpose it. And then the Y will just be the redshifts. And we'll do the same thing for the test data. And then we have a 505,000 by 4 array and a 200,000 by 4 array. So now we're going to do our Gaussian naive Bayes classifier. So we'll instantiate that, we'll fit it on the training data, and then we'll predict on the testing data. And as you can see, it's pretty fast, even though there's 500,000 points. It runs in a fraction of a second.
Why?
Yeah?
Does the redshift tell us the identity of the thing, or this doesn't seem to jive with
Oh,
what we
yeah.
found earlier between quasars and
Oh, I forgot to do that. Yeah, so redshift, the redshift tells you whether something's in the galaxy or out of the galaxy. So I glossed over that. So if the redshift is greater than 0, then we know that it's a quasar. And if the redshift is 0, then we know that it's a star. And that's just within the data pipeline. So thanks for mentioning that. So what we've done is we've taken the redshift, which is a continuous number, and we've turned it into a yes or no. Is it extragalactic or is it here? And the reason we can do that is because these objects have already been selected to be point sources. So we've taken out all the galaxies and things that look like that. So we know it's either a star like this or a quasar like that. Good question. Okay, so once again, we've trained our naive Bayes, we fit it, we predict on the test, and now we can check the accuracy. So we want to see out of the total test points, how many of these have the test equal to the prediction. So we print accuracy, and our accuracy is about 61%. So, but the problem is this, in this case, the accuracy doesn't tell us everything that we want to know. Let's look at how many stars there are in the set and how many quasars there are in the set. We have 186,000 stars and we have 13,000 quasars. So what we need is something. So just the bare accuracy doesn't always tell us exactly what we want, right? Because we could miss every single quasar. If I just labeled everything a star and nothing a quasar, that would give us an accuracy of about, like 95%. Right? So it's silly to just think about accuracy. So we need something a little bit different. So what we're going to look at is the precision and the recall. And basically, in this case, the positives are quasars, the negatives are stars. Positives are usually the things that are more rare. We want to identify the rare things. So we ask about the precision. So what percentage of things that we identified as quasars are actual quasars? And then we also have the recall, which is out of all the quasars in the sample, how many of them did we get correct? And we can calculate these by hand here by finding the true positives, false negatives, and computing that. But it's hard to remember all that all the time, so I don't want to type all this stuff all the time. So instead, I just, you can import metrics from Scikit-Learn, from Sklearn import metrics, and we have precision score and recall score right there. And that'll tell you that our precision is 14%. So, so that means of the, I always get this confused, let me remember this. Of the objects that we classified as quasars, only 14% of them are really quasars, right? So we haven't done well. But the recall is good, you know, of all the quasars in the sample, we correctly identified 94% of them. So it's just a different way of looking at the results, and you have to keep this in mind, that just the accuracy is not always good enough. One way to combine the precision and the recall is the F1 score, which is just, this is how you compute it right there, but there's metrics.f1 score that'll show that for you. And that basically, that combines the two, and F1 score of 0 is bad, and F1 score of 1 is perfect. And we're at about 0.25, so we're not doing so well overall. And if you want all these together, you can use the metrics and type metrics.classification report, and that'll just give you this nice table that tells you about the precision and the recall for each object in your class. So our F1 score for stars, we're basically doing pretty well for stars, and we're doing not so well for quasars at this point. So, and really what this is an indication of is that the model is not good enough. Our Gaussian naive Bayes is too naive. And in the example later on, when we get to that, we'll take a look at how to improve that, how to make the model a little bit more complicated. And from that, we can do a better job classifying these objects. Okay. So that's one astronomy classification task. Any questions before we move to the regression task? Yeah.
I don't understand the recall of stars. That you're saying recall is if you correctly.
Yeah, recall means out of.
Yeah, it seems low, right?
Sensitivity? Yeah, I guess so. I'm confused by that right now.
Yeah, can precision and recall be recast as sensitivity and specificity? Are those the same things? Or no, they're not.
And then people also use, yeah, there are all sorts of names for these different errors.
If you go to the Wikipedia for rock curve, you get all of the.
Oh yeah? Let's do that. Rock curve. Let's check that out.
Is recall the 1% that you got wrong?
Oh yeah. Yeah, that's nice. I like that. So recall is the. I'm gonna have trouble thinking on my feet right now, actually. So maybe I just won't answer it, and I'll leave that as a.
You've correctly identified as quasars, 94%, and the other ones you labeled as stars.
Okay.
95%. And of all the stars in the data set, you correctly labeled as stars 60% of them, but you labeled the other the quasars, which is how you got such a good quasar recall.
Okay.
Also got very poor.
Very well said. Okay, so of all the stars in the data set, we've correctly identified 60% of them, and the rest of them we labeled quasars. And so.
It's based on everything.
Yeah, yeah. Okay, good. Other question?
I think there's a lot of situations where you might want to.
Precision or recall is more important.
Yeah.
And is there, I see like with the F1 seems like a kind of a generic thing. Are there other like versions of that or do you just do it by hand by saying, okay, I care more about precision, so I'm going to focus on precision?
That's a good question. So he's saying sometimes precision or recall is more important, and F1 combines the two. I'm sure there are other measures out there, but yeah, false alarm rate, false detection rate, yeah.
You can also adjust the F-score measure instead of being F1 to being any parameter.
Yeah.
Basically, you add a weight value in the denominator. If it's greater than 1, you have like F2 or F3, or you have
Okay.
F5.
Okay.
That shifts the score to favor precision over recall.
Okay, so you can shift the F1 score. I didn't know that. Thanks.
It's a general family of F-scores.
Cool. Yeah, so, but you're absolutely right that sometimes you want to favor one over the other, and it really depends on your application.
So
Other
here, if you were going to like follow through it and have some person look at the quasars, you might want to get a high recall.
Yeah, yeah. Yeah, especially if it's a grad student looking through, you just throw it. You don't care about precision at all. Yeah, okay. Great. Well, let's, so this is a classification example. Let's move on to a regression example. So I think we did everything on the classification page. Yep, it's all duplicated in the notebook. And if we go to regression, this gets back to the redshift we were looking at before. Say, what if you're concerned with actually predicting the redshift of a galaxy from its photometry? And so I'll tell you what we mean by redshift here. The redshift has to do with the Hubble expansion of the universe. So as from the Big Bang, the universe is expanding. And what that means is that distant galaxies are receding from us. And it's, in some ways, you can view it as kind of a Doppler shift of the light. So the same way as an ambulance is passing you on the street, you hear the siren going high, and then as it passes you, it goes meow and goes low, right? So that's a Doppler shift of sound. The expansion of space induces kind of a Doppler shift of light. And if there are any physicists here, they'll probably yell at me for calling it a Doppler shift because it's not really that, but you can think of it that way. But what that means, since the universe is uniformly expanding, it means that the further away an object is, the larger its redshift is. Because something close to us is not expanding very fast, but something far away has a lot of space in between, is expanding much faster. So what that means is that the redshift of a galaxy is correlated with its distance. And this is very important. So these studies of things like dark energy and dark matter and the beginning of the age of the universe, the makeup of the universe, all that, it depends highly on having accurate distance measurements or actually accurate redshifts and distance measurements to objects in the universe. So this problem right here is something that we're going to do a simple version of it, but it's something that there are papers every month being published on how to improve these regression methods. And the problem we're going to look at is what's called photometric redshift. And so as you can imagine, spectroscopic redshift, finding the redshift from the spectrum is pretty easy to do. So this is kind of a toy example, but if you took the star Vega that we looked at the spectrum earlier and put it out somewhere in the universe, and assuming we could still see it, the redshift would move the spectrum to the red. It basically stretches out the wavelength and moves it to the red. And so in order to measure the redshift, you need some sort of milepost or something that you can measure relative to. And what we measure relative to is we look at the locations of these hydrogen lines, which have a specific footprint, specific wavelengths that those hydrogen absorbs. And as it's redshifted, those wavelengths are shifted to the side. So we can find the actual redshift from the location of those hydrogen lines. And it's very easy to do with spectra because you know exactly where those lines are. The problem is when you have photometry, when you're just looking at the U, G, R, I, and Z filters, it gets much harder because you can't actually, in those filters, you can't actually see the sharp lines, and you have to use basically more the shape of the overall spectrum. And this is complicated by the fact that every spectrum intrinsically is slightly different. So imagine looking at this redshift, but you're changing the shape, you're changing the absorption, you're changing the magnitude, and from these 5 measurements, you're trying to infer the redshift. It's kind of amazing that we can even do it at all, and it was only about 15 years ago that the astronomical community actually started believing the machine learners who said they were doing this. But for future surveys, like the Large Synoptic Survey Telescope, see, this is what happens. I just go off because I'm so excited about it. But the Large Synoptic Survey Telescope is something I'm helping to work on. It'll start in 2018, and it's going to look at the southern sky every night over the course of 10 years. It'll take 3 nights to map the whole sky and then just repeat it over and over. So we'll have about 1,000 observations of the night sky over 10 years. Of the full night sky. And what that leads to is about 30 terabytes of data per night that they're trying to process. And they don't have time to take spectra of all these objects like this, so they're doing everything with photometry. And they're planning on doing their precision cosmology with photometric redshifts. So basically, they need to apply sophisticated machine learning tools to the data in order to get the science results out and learn about things like dark energy and dark matter. So this is very useful stuff. It's not just an exercise. So there, everything I said is right here. So let's pull up the notebook number 8 and look at regression for photometric redshifts. So as with before, if you got the data off the memory stick, you're fine. It should be there, but otherwise you'll have to run the fetch algorithm or the fetch script to get the data off the web. We'll define the data home again, and then load the data set. And let's see again, this is a record array, and we'll look at the names. We have UGRIZ, we have the spectral class, which is the type of object that it is. We have the redshift measured from the spectrum, and then we have the redshift error from the spectral measurement. So we're going to do our same, set up the same sort of data before with our U minus G. And this is logarithmic. UGRIZ are logarithmic, so subtracting them gives you the log of the ratio. So UGRIZ, we subtract them, and then our unknown, or the thing we're training on, is the redshift. And again, we'll split the data into 2 samples. This time, just because I wanted to, I'm going to use 75% as the training sample and 25% as the test sample. And notice we'll do that right there. So we're going to use something here called a decision tree regressor. And what a decision tree regressor does is it's a very fast algorithm, and that's why I'm using it, because we have, let's see, how long is this? Length Z. Yeah, we have 411,000 training samples. So some of the more sophisticated algorithms would take a long time to train, but a decision tree is something that's very quick. It basically makes a series of binary choices. So it's motivated by what people do to classify maybe biological species. So you say, is this a plant or an animal? Animal. Does this have 4 legs or 2 legs? 2 legs. Does this have fur or no fur? And you go on down, and eventually you find out that it's some obscure species of duck. And so it's the same way, except we're splitting things into categories of redshift range. So we're going to import the decision tree regressor. We'll say the max depth is 20. That basically says this is how many binary choices we're going to make in our regression. We're going to fit it to the training set, and then we'll predict on the test set. So let's do that quickly and see how long it takes.
So with this regressor, it sounds like it would work just as well if the target data were categories.
Yeah. There's a decision tree classifier that's based on the same machinery, and we're just using the regressor because it's continuous. So that for my machine took about 5 seconds to run. It might take longer on yours or shorter depending on how new your machine is. So now we have the predictions for the test data, and we want to take we'll do the RMS again, the root mean square, and print that. And we find that it's plus or minus 0.22. So that's okay. For LSST, question.
The same prediction for every element that goes to the same leaf node? Like the
same prediction for every element that...
Yeah, so if you have a bunch of examples that you're predicting on, and you say you have 10 of them that go in the same, lines.
Yeah. So every item that ends up in one bin gets the same result. But since we're doing 20 bins, that means your precision is 1 part in 2 to the 20, so it's like 1 in a 0.00001, something like that. So that could be a problem, but you can change that by just going deeper into the tree. Yeah. Yeah. So what we would aim for, what future surveys are hoping to do, is about 0.01 or better. So, we've just done a simple algorithm in 5 seconds here, and we haven't done so well, but we'll be able to improve that.
What's the kind of variance if you do on this spectrograph? What's the kind of...
Spectrograph is they're accurate to 1 part in 10 to the 4, something like that. Yeah. So actually, we can look at that if we want. If we print? Where was our data? Oh, data redshift error. We can see what typical errors are. Yeah, it's 1 part in 10 to the 4. So the other thing is the RMS, like before, where it didn't tell the whole story. The RMS doesn't tell the whole story here. We also are worried about catastrophic errors, things where the prediction is completely wrong. So let's look at all the catastrophic errors, places where the test minus prediction is greater than 1 or so. We find that out of all 102,000, there are about 1,500 where we have this catastrophic error and it turns out that in terms of learning about dark energy, that sort of thing, in these projects, catastrophic errors are much worse than just having a high RMS. Yeah.
Is there any reason you picked 1 as your...
No, just because there's... I think the redshift spans about 1.5 or so, but there's no reason I picked 1. It's just to see how many there are that are high. So, as before, we can get a more intuitive feel of what's going on by plotting some of this. So I'm going to scatter the test versus the predictions, and we'll plot those, and then I'm just making sure I'm also going to plot the RMS plus or minus. And it takes just a second, but we'll see there that this is the true value on the x-axis and the predicted value on the y-axis. So we're seeing that for the most part, we're getting a lot of them within plus or minus 1 sigma. This red line here is the RMS value, plus or minus RMS. So most of them are getting within plus or minus RMS, but there are clusters of things that are being not very well identified. And these are what we would call the catastrophic outliers. So maybe greater than 1 isn't quite the best thing to use. Maybe greater than 3 sigma or something like that. So this just shows you that how a basic algorithm like a decision tree can be used. And we chose a depth of 20 on the decision tree. And that's kind of the complexity parameter. If you choose a depth of, it's similar to our degree in our polynomial we were using earlier. If you use a depth of 2, then you classify everything into about 4 categories, and you're underfitting the data. If you use a depth of 100, then basically every training sample has its own bin, and any test sample would not really be fit very well. So we can do the same sort of thing with the learning curves that we did before to fine-tune this regression algorithm. And that's actually the second exercise later on, which we might still have time to get to, is working on that. Yeah.
What's the R in front of the string?
That's R means raw. Yeah, raw. So this /m might turn into a weird character if you didn't have the R. Yeah. So any questions on that before we move forward? Yeah, okay. So I think I've been a little overzealous about how much we could do in this time. So the next category here is dimensionality reduction. We've already talked about that a little bit. But this is just doing dimensionality reduction of spectra, basically taking those spectra we showed and projecting them onto a lower dimension to visualize them. And I think I will skip this because the exercises will be more interesting. But if you're curious about unsupervised learning, you can come back to this. So the exercises, there are a couple things, and actually I think what I'm going to recommend is that we don't all work on the same thing, but choose which one you'd like to do. So let me tell you what the three are. So the first one is more photometric classification. It's the same thing, looking at stars versus quasars. But we're going to set up, remember we use Gaussian naive Bayes, which is a very unsophisticated estimator. So this exercise will walk you through creating a more sophisticated estimator that will do a better job of separating out stars and quasars. And that's in this number 10 notebook. The second exercise is photometric redshifts with decision trees. What we just talked about, walk you through basically exploring the learning curve things that we did earlier in order to choose the best decision tree to fit our data. And then also it'll go through some generalizations to decision trees called, there are things called random forests and boosted decision trees. I'm glad you guys know what I'm talking about. So it's interesting, and we can actually pretty significantly improve the decision tree regression for the redshift problem. And then the third exercise is dimensionality reduction. So if you were really excited by principal component analysis earlier, this is the stuff. There's a little bit of that in there. Principal component analysis of spectra, and then moving on into some newer variants and newer extensions to dimensionality reduction routines that do actually nonlinear dimensionality reduction. It's manifold learning, things like isomap and locally linear embedding. So all three of these are available, and we have just about 45 minutes left. I think that should be enough time for you to get through one exercise, maybe start on another. And I'll leave it up to you which of the three you choose, whichever interests you the best. And I will be walking around to answer questions. But I see one hand right here.
I
Yeah.
have one general question about getting your data ready. Like, for example, the earlier exercise where we had those 8x8 bitmaps of the numbers. Now, that's nice and neat. What if you had 8x8, 12x12? You had they're not uniform, but you're still trying to do the same basic thing on that. So what do you do in those?
Yeah, in that case, if you had images that weren't all the same size, you'd have to do some sort of interpolation and get them all to the same size. Yeah, and that's not always the easiest thing to tell, right? Because for the digits thing, let's say you had one. This was 8x8 like this, and then you have another one that's like this, and there's your digit right there. I mean, how do you don't want to just interpolate, right? You want to make sure. So for digits and facial recognition and things like that, and even for astronomy, there are often pre-processing steps. So you'd do some sort of feature finder that would center your digit there, and then you would interpolate to an 8x8 grid. So things are really involved, and you'll notice with the astronomy examples as well. We just assumed that you had already found all those million stars on the image, and there are programs that are used to do that, or you can try to create your own. It's pretty fun, actually. Before we break into the exercises, any more general questions about this whole thing? Because I probably won't be talking at you anymore. Yeah.
This might be probably like a very involved answer, and so you just say, yeah. What do you think about, what are Scikit-Learn's facilities for like feature extraction?
There's the feature extraction module. He was asking about what Scikit-Learn has as far as feature extraction. There's a feature extraction module that is being worked on a lot. I don't think it's quite mature yet. But it has some things in there for textual feature extraction. I'm honestly not too familiar with what's in there, but it's mostly looking how to extract features from text documents, because other than text, most other data is pretty straightforward to find features. Yeah, but that's another one of those things that I think we're waiting to become more mature before doing a 1.0 release. Yeah. Yeah.
Following up on that, is it mostly, who are the communities that are driving the Scikit development?
Yeah, he asked who's the community that's driving Scikit-Learn. So it's basically the bulk of the people are in Europe. It's gotten a lot of support from INRIA, which is, yeah, it's Gaël I can never say his last name. It's French. He's the guy that's been kind of heading it for the last few years, and so because of that, a lot of the development team is in Europe, and there are a few of us, David and myself, and maybe some others in here who are stateside or in Canada. But it's.
None of those guys are here, right? At the conference?
I don't think any of them came this year.
EuroSci-Pi.
EuroSci-Pi, yeah, that's the
place. I was debating which one to go to.
Yeah. So it's pretty much volunteer driven, except for one paid intern position in Paris, and a lot of stuff has been done. It has, I think Scikit-Learn has a really strong base of contributors from all over. Lots of people who do little things, whereas other packages tend to have a few people who do lots of things. And I think it's well supported that way. Does that answer your question?
Well, I was kind of wondering what the applications that are driving.
Oh, what applications are driving this? Yeah. Yeah, so the question is what applications are driving this. I think a lot of it comes from neuroimaging, and that's INRIA's influence. But there are also people who are just interested in machine learning in general. We have several PhD students who are doing PhDs in computer science, studying various machine learning methods, who want to just make their methods available. I come at it from astronomy. I think other people come from other situations. But the reason I got involved is because I was looking for some specific algorithms for my astronomical research, and there weren't any good ones available. So I spent some time writing them, and then I thought, well, this is stupid for me to write it and not make it available to anyone else. So I started poking around, and Scikit-Learn was the place for them. So I'd encourage you guys all to, if you're interested, to contribute. There's some very easy entry-level things that you can do to contribute to Scikit-Learn, and I'm planning to have a Scikit-Learn sprint on, Friday and Saturday.
Yeah, so about the sprints, do we know anything about this, or?
I don't know yet.
Okay.
I think the sprint stuff will be announced in the main conference.
Proposals.
Yeah, just assume that.
You got a few up right now.
Okay, so I'm going to let you guys, one more.
Does Scikit have the ability to create simulated data to work with?
Yeah, there's a lot in that datasets module. There's archived data that can be downloaded, and there's also simulated data, various standard simulated sets.
Well, but a way to build new simulated data.
No, I don't think there's anything in Scikit-Learn for that, but I mean there's probably tools in NumPy and SciPy for that sort of thing.
Yeah, I've been working on one of these issues, and there's a main data set function somewhere.
Yeah, there's a couple, but I guess I'm not sure exactly what sort of simulations you have in mind.
Yeah, I mean, you would want a different sort of simulation to test different assumptions. Different estimators.
Yeah.
You know, one size fits all.
Yeah. So what if we?
You're wanting something like in optimization stuff, you can like put test functions or like you want to think kind of like that, but for general problems.
Yeah, so we can make blobs, make circles, make Friedman. So these are the sorts of things that are in Scikit-Learn. Yeah, so it's definitely not a complete list, but there's several things in there that are useful in different situations. Yeah. Okay, I'll let you guys choose your exercise and work on it. I'm going to be walking around, and feel free to ask any question or grill me or whatever you want to do. And I'll round us back up in about probably half an hour, just for closing remarks and tearful goodbyes and all that, and it'll be great. So go ahead. The GitHub page, github.com/Scikit-Learn. This is where all the development takes place, and you can click on the main Scikit-Learn repository. And the easiest entry is just to click on this Issues button right up here, and that'll show a list of all the bug reports, all the features requests, and different things going on. And there's an easy fix tag, and several of these are easy fixes right now. And these are just things that need to be done. There are various levels of commitment, but they basically require someone who knows how to code in Python. And we'd love to have you contribute. It's always fun to have more people thinking about this stuff and testing it. And if it's something you're interested in, talk with me. I'm also planning to do a sprint on Friday, whenever the sprints are. Do a Scikit-Learn sprint that day. So thanks very much, and I hope you found this helpful. I'd love some feedback if you want to find me during some of the coffee times this week and let me know what you thought and what you thought was good and what I could improve in the future. That would be great. And right now, I think Warren has an announcement real quick. Yeah. In this tutorial, you can click on them, and it has the Python code that was used to generate them. So in case you want to see the nitty-gritty of how things were put together. So let's talk first about features and feature extraction. So as I said before, every data set in Scikit-Learn is assumed to be a matrix or an array, a two-dimensional array. That's the number of samples by the number of features. So that's the shape of the array. And by number of samples, I mean different objects. So we're going to be talking about astronomy later. So maybe the number of samples would be the number of galaxies or the number of stars you observe. And then the number of features is independent measurements you have of each of those objects. So if you're looking at stars, you might take an image of that star through a red filter, through a blue filter, through a green filter, and a yellow filter, say. So then you would have 4 features for each object, and you might observe 1 million galaxies, so that would be 1 million samples. So your data set would end up being a 1 million by 4 array. So that's typically what Scikit-Learn expects. So we'll do a quick example here, and Scikit-Learn has a number of basic examples that data sets that are just built in that we can play with. So we're going to go to the first notebook, the datasets.ipynb, and click on that, and we'll see this right here. So this will just show you basically how to work with data from the Scikit-Learn. So we're looking at data from the iris data set. So this is observing the characteristics of a bunch of flowers in nature. And based on what the characteristics of those flowers, we're trying to classify what species those flowers belong to. Yeah, if you go, so once again, the IPython notebook, if you change directory to the notebooks directory, either in the GitHub repository or in that file that I gave you on the data stick. And then you type IPython notebook and press enter. You should see this page right here. Everyone good? Cool. So once again, you click on the first one, data sets, and we'll see this right here. Nope, not that. This. So we're looking at irises, flowers with different features, and the features in this data set are the length of petals and sepals, various parts of the irises. You know, scientists went out and measured those with a ruler, I guess. That's how you'd measure irises. And so there are 4 features, and then the targets are one of 3 different species. So the first thing we do is from sklearn.datasets, we import load iris and then call that. And this will load the iris dataset. And just as an aside, if you want to see what other datasets are available, you can just type sklearn.datasets ? And then, actually, sklearn datasets dot and then press tab. What did I do wrong here? I did. Yeah, there it is. Dot tab. I'm doing something wrong. Well, we'll see that later. Sorry about that. Okay, so we've loaded the iris data set, right? And we're going to look at what the number of samples and the number of features are in this data set. So that's in the data attribute. That's the array where the data is kept. And the shape is the number of samples and number of features. So we see there are 150 samples, 4 features. And if we look at the first sample, these are what the features are. So basically the sepal length is 5.1 centimeters. The petal length is 1.4 centimeters. Now, before we move on to the next part. Yeah.
We're kind of talking here about setting up the kind of truth data set.
Well, we're talking about setting up any data set. You can, in this case, this is the truth data set because we have the labels for each one. We know that this is a 0. But we'll also have, we also might have unknown samples, but we just need to make sure we break them up the same way. So if you have an unknown sample, in this case, you would need to run some sort of algorithm to find the digit on the page, to break it up into an 8x8 image, and then that's your set of features. Because let's say you have, if you have this as your training sample, if you have this set of images that's 64 pixels, and you have some more digits that you want to classify that are maybe 144 pixels, or 12 by 12, then the machine learning task won't really know what to do with that, because how do you compare 64 features to 144 features, right? So you have to make sure all your data is in the same format. And in this case, this is the training set, but it could be the unknown set if it just didn't have these labels. If we either forget that we know them, or if we don't know them. And we'll see some examples of that later. Does that answer your question, Matt?
Yeah.
Good, thanks. All right, so let's close this notebook. It'll ask you if you want to stay on the page. That's just whether you want to save all the changes that you've done. I don't want to save the changes, so I'm going to leave the page here. And we'll go back to here. So that was actually just a bit of an aside about data sets and how they work within Scikit-Learn. So I find that when there's a new algorithm in Scikit-Learn that I want to try, when someone's submitted something in a pull request and that sort of thing, I can go back to one of these data sets that's available, like the irises or like the digits, and just try it out, see how it works, see how it compares to things I've used before. And it's a really nice way to do that. I should also say, as we're looking into this, if you go to www.scikit-learn.org, this is the Scikit-Learn documentation, and there are a lot of examples here as well that use these built-in data sets. So, for example, recognizing handwritten digits. This is similar to what we just did. They're looking at the exact same data set, but it just gives you an example of how you would actually go about classifying this data set. And all sorts of other things here. There are tons of examples that you can peruse through. And I've found that whenever there's something that I need to do with my data, I can just go to this examples page. It's basically that top tab at scikit-learn.org. Go to this examples page and just look through and see what sort of things are available and if there's anything that matches the type of problem that I want to do. So that can be really useful. but let's go back. So where are we? So we're looking at general concepts. Okay, so Matt's question earlier touched on this. So we talked about the training set and the test set. And that goes into the different classes of machine learning. So we're going to talk here about supervised learning, the differences between supervised learning, unsupervised learning, and how that affects the Scikit-Learn syntax. So basically, the two classes are, if supervised learning is the case where you have a set of objects where you know the true value, you know the true label, and then you have another set of objects where you don't know the true label, and you want to figure out what the label is for that unknown set. So for example, with the digits we were looking. Oh, you download it? Yeah, if you got it from GitHub, you just go into the doc directory and type make nb convert. Yeah, so let me go down here and show you how it works. So if you're in the doc directory, you do make nb convert, and that'll create all those notebooks for you in the directory. I'll change all the versions. Hopefully I made this as easy as possible. We'll see. Okay, so why don't we get started? We're the way I'm going to work is I'm going to have this web page up in one tab. I'm going to have the notebooks up in another tab, and then I'm also going to have my terminal that I'll come to occasionally, but we probably won't have to use the terminal very much throughout today. So if you can get your tabs set up so you have the web page here and the notebook, that would be great. And I'm going to make it full screen here. Okay, so as by way of introduction, the machine learning, I think, is a tool that can be useful in a lot of different fields. It's been used in a lot of different fields, and my hope is that everybody here, no matter what sort of data you're working with and what sort of application you have, you'll be able to use the tools that we talk about here and work with them within your own field. A few people walking in, did everyone get the memory stick? If there are a couple memory sticks being passed around, where did they end up? I think there's a few new people that need them. The memory stick has some data files on it that we'll be using a little bit later. Okay, so I think most of I'm going to click on tutorial setup and installation right now. I think most of what I've said already is in here, and hopefully everyone has these prerequisites installed. This download the datasets part, running the fetch data.py, you don't need to do that if you got everything from the little memory stick I was passing around. That already had the datasets there. So let's go on to the next and get into the content. So let's talk about general concepts. So for this first section, I want to make sure that so Scikit-Learn, when you're dealing with data, it expects a certain data format. And so we're going to talk a little bit about how you might extract features from real-world data that can be used in that format. And it's a simple format. It's just a matrix, the number of features by the number of samples by the number of features. So every data set in Scikit-Learn is expected to be a two-dimensional array, essentially. So here we're also going to talk about the difference between supervised learning, which includes classification and regression on one hand, and on the other hand we're going to talk about unsupervised learning, which is things like dimensionality reduction, clustering. It can be useful for data visualization and things like that. And also we're going to play around and understand the difference between a problem that's linear and a problem that's nonlinear, because that ends up being important. So basically this plot right here shows you basically what machine learning is all about. You have two data sets, or you have one data set that has some different labels, and you're trying to find some way to classify them. This is what we would call a classification problem, where you have, it's one big data set in 2 dimensions, and we can plot it on a graph like this. The colors are the labels of each point, and one machine learning task might be asking to find the best dividing line between these 2 classes. So this is a typical classification problem, and we'll get into that later. Just a side note, if you're ever curious, any of the images, etc. So that's what we're looking at. This is how we've taken our real-world data set and put it into a format that Scikit-Learn can use. Okay.
I'm sorry to get
Yeah.
away. When I open up the notebook, I just get a blank thing, even though I click on the data set. Is there some obvious thing I'm supposed to do?
Oh, do you have try loading the version 2 of it, because you might be running an older older IPython. So yeah, if you're running an older version of IPython, you might need to click on .v2 to make that pop up. Does that work for you?
I don't actually see it.
Running no script,
No script?
no script, you have JavaScript blocker. You have to turn that off.
Oh, really? Okay.
You have to run JavaScript.
Okay, so maybe that's the problem. Are you blocking JavaScript? Okay, thanks.
I had a similar problem. I just upgraded to 13.
Oh, really? Okay. Okay. So I think one person said if they had that problem, they upgraded to 13 and it was okay. Okay, so we're looking. We have the iris.data, which is those set of feature measurements, and then the iris.target is the set of applications for the training set. So we look at the length of those 2. They're the same, which is good. And looking at the target, it's basically a numerical classification, and this is pretty common in Scikit-Learn too. We don't have a way we don't want to put an array with the name of each of those species. We don't want an array full of iris setosa, iris versicolor, because it's not numerical. The method wouldn't know what to do with it. So we encode those features as basically, or those classifications as numbers, either 0, 1, or 2. And in the iris data set, we have the list of target names, and that's basically the species names here. So the classification, the numbers are set up so that you can, they're basically the index in the list of the target names. Yeah, so also, this is just another aside about how Scikit-Learn works. When you load these built-in data sets, they'll be saved onto your disk in this location. If you run get data home, it shows you the default location where that data is being stored, and that'll all be done in the background when you type fetch underscore whatever the data set is. So this is what I was trying to show earlier. If you do data sets from Scikit-Learn, import datasets dot fetch underscore, and hopefully if this, I don't know why this isn't working right now. There we go. Yeah, so if you run import datasets, then do datasets.fetch underscore and type tab, it will show you what sort of datasets are in there that you can play around with. And some of these are pretty fun, like the Olivetti faces. That's a database of facial images, and you can practice basically identifying people in images. And there are some good tutorials online for how to do that, but we're not going to do that right now. Okay, so just as another example, this is a fun one, the digits data. We're gonna use the load digits functionality to load this set of basically images of handwritten digits. If we take a look at this right here, looking at the number of samples and the number of features in the digits data set, we can see that we have 1,700 or about 1,800 samples, so about 1,800 images of digits, and each one has 64 features. So you might wonder what those features are in this shape, in this case. And we can, just to look at the first example here, this is what the features look like. It's just a series of 64 numbers. And the target is the number 0 through 9. So we're essentially looking at these samples that each have 64 features that represent a digit. And then the classification, the label is the number 0 through 9 that it's supposed to represent. So to show you what these features are here, you can run pylab inline. This percent here, this is a magic command in IPython. So it's something, it indicates that it's something that's not available in the normal Python interpreter, but it's something that had been added in IPython for convenience. And what I'm doing here, we'll see this a lot through the tutorial. When I run pylab inline, that's saying that all plots I want to appear inside the notebook rather than popping up a new window. So it'll just make things more convenient. Oh, I should also say, I forgot to mention this earlier. As we go along, be sure to, within each box that we go through, be sure to press Shift-Enter to actually run the code. Because if you don't run it earlier, then later on there might be variables that are undefined. So as we step through this, try to keep up and press Shift-Enter. So what I'm going to do right here is, this is just a quick code that'll show the digits. And what we're doing is we're cycling through the first 100 of these samples, and we're going to add a little subplot to our plot. And then we're going to take the ith sample and reshape it into an 8x8 array, and then show that as an image. And this will show you what the digits data set is. And it takes just a second because it's got to compute all that stuff. Oh, I'm wondering if it's, oh, there we go. So the digits data set is a set of pictures, and we have the labels that go with them there. So these are 8x8 pixel images that show some handwritten digits. So this just gives you an idea of how you could, if you're looking at images, this is how you would break up an image to be readable into Scikit-Learn for machine learning. You're basically taking each pixel as a feature. So if you have 8x8 pixels, then that's 8 times 8, which is 64 features. And so these digits, even though this is where it can get sometimes confusing, each sample is a two-dimensional array, but you flatten that array into basically a 64 element vector, and then you stack all those on top of each other so that this digits data set becomes 1,800 samples by 64 features. So some of the art in machine learning is sometimes can be figuring out what the features are that you're trying to look at. And for example, in some astronomy situations, we've measured thousands and thousands of features of a data set. And it might be that all those are useful, but it might be that you want to select some of them rather than others. And it really depends on the algorithm you're running, and it depends on what your goal is in doing the learning problem. So any questions about about Scikit-Learn's data representation at this point? The fetching data, the displaying data? Yeah?
I never got the data sets dot fetch underscore to module object that has no attribute fetch.
Oh, really?
Well,
Oh, okay.
it doesn't have exactly that, but that's just the prefix of a bunch of functions in the module.
Yeah, so
Yeah, or IPython, if you hit tab, IPython will pop up a little window that shows you all the
Here we go. Yes, yes.
yeah, so that's a tab completion rather than execution. Thanks. Any other questions? Right.